Hello everyone, today we'll be going over the Blind 75 in C++, and really we're just focusing on the full course today, meaning we are going to be tackling every single problem in C++ for the Blind 75 on Leetcode, and without any further hesitation, let's get started. Hello everyone, today we are going over some Blind 75 in C++, and today we will be focusing on product of array except self. So, before we get started, I'm just going to stick with our formulation really quick. Hang on, I just practiced this earlier. For any of these type of questions, there are 4 questions we would ask. Our input, what data structure / algorithm or technique we're going to use, and what are we going to do with the data, and then what is our output going to be. So with our following question that we have, given an integer of array nums, return an array answer such that answer I is equal to the product of all the elements of nums except nums of I. So going over that question, we've already answered our input and what our output's going to be. We are 1, given an array of nums, and our output is that we need to return an array where the answer of I for each index is equal to the product of all the elements of nums except nums of I, and the following 2 constraints that we have as listed below. The product of any prefix or suffix of nums is guaranteed to fit a 32-bit integer, and you must write an algorithm that runs O of n constant time and without using the division operation. Okay, so to be able to go over the example that we have, to understand the relationship of the question, is that we have first an array of nums, and what they want us to do is replicate this type of behavior where we have every single index that we have, each element is going to be replaced by the product of the other elements in the array. So say for instance we have the output of 24. When we mean product, we mean we are going to multiply every single number that is not the element. That's what they mean by product. So if we are at nums of 0, that's going to be 1 at the 0 index, and so 1's going to be replaced by the product of 2, 3, and 4, which is going to be 2 times 3 is 6, and 6 times 4 is going to be 24. And this relationship can also be conduced for the other ones. If we're at nums of 1, where it's going to be 2, we're going to multiply 1 times 3 times 4, which will then be 12. And then we can also just do the same for 3. So it could be 1 times 2 times 4, which is going to be 8, and 8's going to replace the 3 that's up here. And then finally for 4, we are going to replace 4 with the product of 1, 2, and then 3, which would then be 6. And this relationship can also be the same as well for each one, such as we replace -1 with the product of 1, 0, -3, and 3, which would therefore be 0. Then also do the same thing for 1, where we replace 1 with the product of -1, 0, -3, and 3, which would then be 0 altogether. And then we can also do the same for 0 at this index. We're going to replace 0 with the product of -1, 1, -3, 3, which would then be 9. And then we would have the other ones be 0 and 0, because we replaced this with the product of these numbers, and replace this one with the product of these numbers, which would therefore be 0. Okay, so we understand the relationship of what we do. So the output for when we are returning an array, what is this breakpoint over here? Okay, that's weird. Okay, we return an array where each, where nums of I is replaced by the product rest of the elements multiplied So we return an array where nums of I is replaced by the product of the rest of the elements multiplied. And then we will also work through our example to help break down the entire problem altogether. And so the data structure / algorithm we're going to use is called the prefix and suffix product arrays technique. So prefix and suffix product arrays technique. And some may wonder initially, and I thought of this myself, what about two-pointer? Well, I've heard of this thing called two-pointer, but isn't that the same as the prefix and suffix product arrays technique? Well, actually, no, it's not. You see, the differences between 2 pointers is that we're focusing on really just the whole array all of itself, and we're going to be focusing on the left and right side of the array, not particularly 2 points in the array. We are going to be scanning and creating 2 different arrays to be able to keep track of what we have already done. So to answer, what are we going to do with the data? We are going to first create 2 arrays, which will then be vectors in C++, to store all the elements. Store all the elements visited. Create 1 array. In fact, I'm just going to put this inside of the technique so that way we know exactly what to do. Right over here. So we would first create 2 arrays to store all the elements visited, create 1 array for the left side visited, and then create 1 array for the right side visited. And then finally, what are we going to do with the data? We will loop through our given array, create both the left and the right side arrays, by creating a formula to take the index of each element and store them in their respective arrays, then multiply both the right and left side arrays we created for the output array. That is what we are going to do. So to kick things off, what I am going to be doing is that I will be, for step 1, we will create 2 arrays to keep track. Is that I'm going to create a vector where it behaves similar to an array, but it keeps everything way more organized to be able to start. And I could initialize nums initially, but for the sake of clarity, I'm just going to do 1 and then nums.size, because we're creating a vector or array, so to speak, that's going to be the same size as num, and then I'm going to create 1 for the right side, and now we're going to discern the relationship between the 2. So we're going to create the left array, and then we will eventually create the right array. So what we will be doing is, first things first, is that for our left array, what we will be doing is that we are going to have this relationship already set where int I is going to be 1, since we're starting off at 1 element. We're starting off at the element that is not going to be the leftmost, because we need to find the product of every single other element that is not going to be directly of nums of I. So we're going to multiply every single product to be able to get our output that's going to replace the index of nums of I. So then what I will be doing is then having I is going to be less than nums.size, and then we're going to increment up since we are going on the leftmost side. And the equation for us to be able to do this is that we're going to have left of I is going to be equal to, since we are focusing on the leftmost part of the array and that we are incrementing and we want to focus on the leftmost side as well, without even going in the direct position, we will then have left of I minus 1 times nums of I minus 1. I can explain further in this example. So if we have, say this relationship, and mind you, whenever we initialize an array, it's typically going to be in ones to start with, and then for if we were to start with nums of 1, 2, 3, and 4, we will then have to take a following index. So say, for instance, left of I is going to be like the leftmost in, since we are starting off at 1, we're not going to put 0, so we're going to start 1, and then we're going to have left of 1 is going to be equal to left of 1 minus 1, which will then be 0 times nums of 1 minus 1, which will then be 0, where it's going to be left 0, and then left of nums. And since we don't have anything already set in place for our new array that we're going to create, so left new array, which will then be a left of 1, 2, 3, 4 points. Yeah. It will then have to be, or hang on, nums of 0. So 0, 0. It's then going to be, since we're going to start at 1, it will have to be at least 1 to begin with. And then what we will be doing is that we are also going to be doing left where I is going to be 2. 2, 2. Left of 2 is going to be left of 2 minus 1 times nums of 2 minus 1, and we're going to refer to our array that we have already made since we are creating a leftmost array. Since this is not the initialized one, because even though the initialized one will be 1, 1, 1, 1, this one is going to be a new array that we are creating, and we're just referring to the new array for future calculations as well. So we have a new array, which would therefore be left of 1 times times num of 1. It's therefore going to be, if we have 1 right here, because we start at 0, 1, 2, and 3, for arrays always typically start at 0 by nature, and then we would have, so left of 1 times nums of 1. It's going to be 1 over here, and then it's going to be 2 over here to start. So 1 times 2 is going to be 2. And therefore, the left of 2 will also be 2. Yep, there we go. And so the new array is 0, 1, 2. There we go. And then we'll do the same thing for I is 3. And this should be the very end of our new array. So 3, 3, 3, 3 minus 1, nums 3 minus 1 is going to be 2, and then 2, we refer to our new array that we have already created. Alrighty, so what is left of 2? 0, 1, 2. It's going to be 2, and then we have nums of 2, where that's going to be 0, 1, 2, which would be 3. So therefore, it's going to be 2 times 3, which is then going to be 6. So therefore, left of 3 is going to be equal to 6. Just want to clarify if I got this right. Yep, okay. So it's actually going to be 6 over here. Just wanted to clarify. And then given the fact that we have started at 1 and we are initializing our array, overall the new array at index 0, I'm just going to put this at the top to start. It's going to be reverted to 1. Left of 0. And since we already have this formula already here, it's just really just going to be 1 to begin with. Just going to be 1. Since we've already started at 1 to start with, and we're accounting for the other size of the nums to start with. Because for the leftmost, and according to our relationship that we are exploring, we need to have the product of every other number, except every other index in our array except for the current index that we are on. So this is why we do this in particular of left of 0 will be to 1. So overall our new array altogether is going to be 1, 1, 2, and 6. So that's what we do. And now we're going to focus on creating the right side array, where it's going to have a similar behavior with the left side, It's just that the difference is the way how we treat our for loop to start with. Since we're starting with the rightmost array to begin with, it's going to be int of I is equal to num minus 2. No, it's going to be yes, it is. Size minus 2. The reason being is because we want the rightmost array, we want the rightmost element of our given array, and with the rightmost element of our array, typically if we want the rightmost, we go nums dot size minus 1 to find that very last one to start. But in this case, since we only want the element, we want the product of the other elements except for the element that we are on. We are doing this minus 2 because this is just in respect to the relationship that we want. We want it to be equal to the product of all the elements except of nums of I, which is why we do this minus 2 to start with. And so since we are going on the rightmost side of our given array, we are then going to have this be greater than 0 because it has to be on the rightmost. And then we are decrementing at the same time. And the relationship to begin with is, given the fact that we are doing the opposite of our left side, it's going to be right of I is going to be right of I plus 1, since we are going down, times nums of I plus 1. The reason being, I will explain this relationship further. So whenever we initialize a new array, typically, or vector to start with, what we would do for the most part is a similar retrospect to what we do on the left side. So I'm just going to copy and paste this and put this in here and redeclare at the same time. It's going to be right, and we have nums. So the new right array to begin, I'm just going to get rid of the others, since what we are doing is that we are going to be focusing on the rightmost side. We will start at index of 2 because of this 2 that's already right here. So index of 2, just focusing on this example. So that would be I is equal to 2, right of 2. And since we, this formula, according to what we need to do, right of 2 is going to be equal to right of 2 plus 1 times nums of 2 plus 1, which would be equal to right of 3 plus nums of 3, to therefore be, so 0, 1, 2, 3, that would be right of 3, 0, 1, 2, 3, so that would be 1 times 4, which would then be 4. Yeah, that's correct. And then for the other ones that we will do, since we're going down our array, we're decrementing as indicated by this for loop. For this I, it's going to be 1, and then it's going to be 0. So right of 1, focusing on 1, 1, 1, 1. It's therefore going to be right of 2. Plus nums of 2, and mind you, an important thing that we need to note is that our new array is always going to get updated. So that means our new array will have to be right of 2, so 0, 1, 2, it's going to be 4 to start with, and for any new number we add, we always refer to our new rightmost array. So, mind you, we're bringing this down. If it's going to be right 4, the number is actually going to be 0, 1, 2, which would then be 4 times, how did I put this plus here? It's times, not plus, since we're multiplying the product. So it's going to be 4 times the num of 2, which is 0, 1, 2, which will then be 3, which therefore will be 12. And so therefore, right of 1 is going to be 12. So if we go in our array, 0, 1 is going to be 12. And then finally what we have for 0 is going to be right of 0. Right of 0 is going to be 0 plus 1, 0, plus 1 for nums as well. And so that will be 1, nums of 1. And mind you, we always refer to our new array that is already created for any index that we are creating, because since it's referring to the specific index that we have created while we're decrementing down inside of our array, we will then have to take each number that we have created in our new array to finally have our output eventually. So what we are going to be doing is right of 1 and nums of 1. The right of 1 is 0, 1, which will then be 12. And then, why does this? There we go. There we go. So right of 1 times nums of 1 is going to be 12 times the nums of 1, which would therefore be, going back to our nums array, is going to be 0, 1, which will be 2. Because arrays typically always start at an index of 0, and then they go all the way up. So it would be 12 times 2, which is equal to 24. And right of 0 is therefore equal to 24. And arrays typically start at 0, so we put it right here, 24, 12, and 4. And, mind you, for our third most, since we are focusing on the element except for itself, we're going to go back to our right array, and therefore our rightmost element, very rightmost overall, with right of 3, our rightmost is going to be 1, because we are referring to this rightmost array. Since the question is already stated, we want to return an array such that answer I is equal to the product of all the elements except nums of I. So we need to exclude that one last element, much like in the case of the left, where we exclude the leftmost at the same time, and we just continued up in the array according to our for loop. So that is how we do this part for the rightmost array. Now for the output, since, mind you, I want you to keep in mind about the right and the left at the same time for our array. So our output altogether, we're going to create another array, which it's going to be a vector of int. It's going to be output of nums.size. That's how we create our array to start with. And so we're going to treat this like a regular for loop. I is equal to 0. I is going to be less than nums.size. And then we'll just increment it regularly up and about. And the output of I for each index is going to be the left of I times the right of I for every single element. And it's very, very straightforward to start with. So if I were to have an output is going to be the left of I on you, every single index is going to be multiplied from every single index of left of I and then right of I. So output would be, so say for instance we have output of 0 to start with. It's going to be at the index of a given 0. 1, 2, 3, and we want to have nums. Mind you, we have our rightmost array, our new right array, and then we also have our left array. I just want to be able to highlight this as well. New left array, new right array. So we have left array of 1, 1, 2, and 6, and then right array of 24, 12, and 1 right here, as indicated right here. And then we have our leftmost array as well, indicated right here. We're going to multiply every single one. So if we have output of 0, left of I is going to be left of 0 times right of 0. So it's going to be 24. And then we can do the same thing for the other ones as well. It's very straightforward. But if you have any questions or anything else, feel free to put them in the comment section. 1, 2, 3. And the reason why we do 0, 1, 2, 3 is because we're creating an array based on the size of our nums. So if we refer to this one, it's just referring to the number of indices that we already have, which is why we do this. So if we do 1 and 1, because we replace I that way, 2 of 2, and then 3 of 3. If we look back on exactly between leftmost, so 0 right here, it's going to be 1 times 24, which will then equal 24. Then it's going to be for 1 times 12, which will then be 12. Much like in the case up here, look, 24 and 12, we're getting this relationship. And then 2 and 2, which will therefore be 0, 1, 2, which will then be a 2, 0, 1, to at that element, it's going to be 2 times 4, which will be 8. And then we are going to have left and right of the third. So 0, 1, 2, 3, 6, and 1, which will then be 6 altogether. And so our output array is going to be 24, 12, 8, and 6. All right, so this is how we get our relationship all together. Make sure you always check every single, make sure you put every single syntax correctly. And I think this should be good. Let's run this and see if it works. But don't forget one thing, return the output, because that is what we are looking for ultimately. I just want to make sure everything is already checked. We got our edge cases as well. Let's solve this. Oh, there's some overflow going on. I think my biggest issue that I have oh wait, okay, I messed up because it's supposed to be nums of I and then 1. I apologize immensely on this front. It's supposed to be nums of I. So the reason why it's supposed to be nums.size of I and 1 is because this is how we initialize it. We don't do 1 of num size at all, because if we do that, if we had it initially before, that's a big mistake on my front. That was a big mistake on my front. I apologize on that. So it's going to be of 1 and then nums.size, because actually it's going to be the opposite right here. The reason why it's not this is because we're first initializing the size of a given array, and this doesn't really add up to anything else. Instead, we need to put we are creating at least one vector for each array that we are creating, and we're referring to the number of said arrays at the same time. So this should probably fix it. Yes, right over here. So this is how we initialize each of the vectors. It's going to be the size, and then we have 1 referring to the number of said vectors that would indicate for our arrays. So I will submit this just to double check on this. And so the time complexity for the following solution is going to be O of n, which is constant, and then the space complexity and time complexity are both going to be constant, O of n, because the reason being is we have 2 arrays that we are storing that information set in, and our solution is going to be relative to the size of our given array. So the longer the array, the constant time it would take for the size of the array to actually finish within our program. And there is a way where we can optimize this for time complexity. It's pretty stable since it's an O of n, but the space complexity, we can also further improve on this. We can do this in another technique where we can just have 1 array versus having 2 arrays to start with. So I'm just going to go back on this solution, and yes, make sure everything is already initialized correctly. And what we are going to do is that instead of doing just 2 vectors to start with, we're going to start with 1. We're going to start with just the left side to start with, and then we can actually blend this for loop, the behavior of it, for a vector output as well. Because the reason being is that we can treat the rightmost array in terms of just having 1 to start with. So what we can do is that we're going to first initialize right is going to be equal to 1 to begin with, and then we will take our for loop that we have already have and treat it as if we're going on the rightmost side to start, versus just having a standard array where we are just looping directly forward. So we can just start with nums.size, and then we're going to start on the rightmost side, have that behavior already set in place. It's equal to 0, and then we're going to decrement as well, And inside this for loop, what we will be doing is that we are going to be calling upon the relationship of right and then nums I, because the reason being is that inside of this for loop of what we will have, the right variable is going to update within our for loop and therefore be recalculated inside of our given output while we are returning our output for each index that we have. Since we are creating an array already to start, we will then need to return every single index for our given output as well, right over here. And it should be optimal by keeping everything in linear space complexity, not time. Our time is still going to be constant because we're still using an array, which is a data structure, and it's storing the information while scanning every single element within our given array, and our solution will run relative to the size of a given input of our array. So let me run this really quick. Okay, we have this error because I didn't actually get rid of this entirely. We're getting rid of this entire right. Okay, something's wrong over here. I need to actually fix that. So this will be our solution overall. And make sure everything is already checked. Oh boy. By minus one, because the problem is that we have nums of size and we're getting the rightmost array, and typically in our array we're not going to refer to nums.size. We are going to be doing this type of solution of a for loop, int I equals nums.size minus 1, and then I is greater than or equal to 1, and then I is decremented. Okay, so it runs. There we go. So this is the most optimal solution. It runs in constant time O of n, and then our linear space time is, well, our space complexity is going to be linear, while our time complexity is going to be constant, O of n. And so this would be a further optimal solution as well. I have more descriptions. Let me just go back and just clear up all the rest of the pseudocode just to be able to help just give the clear answer all together. Right here, I just put that in for reference. There we go. So this will be our optimal solution all together. So it runs in linear, the space complexity is going to be O of 1, and the time complexity is going to be constant O of n for the most part for this entire solution that we have. We have our vector that we just use for one. We create the left vector as well, and then we have a vector that will then be our array that we return at the same time. And make sure that all of your code is already cleaned up prior to. At the same time, look for small syntax errors as well. During that, that's also another advice. Apologies if I had some errors along the way. So yeah, that's just pretty much it for product of array except self. If you have any questions down below to further iterate on the solution, feel free to let me know. And thank you again for taking time to watch this video. Like and subscribe, and as always, take care. Hello everyone, today we're going to go over the blind 75 in C++, and today we are working with remove nth node from end of list. Now, before we get started, feel free to pause the video. For whenever we are breaking down our following question, we always need to ask ourselves these 4 questions. What are inputs going to be? What data structure / algorithm / technique to use? What to do with the data? And finally, what are outputs going to be? So, to be able to give a rundown over exactly what this problem entails, just breaking down the problem. Given the head of a linked list, remove the nth node from the end of the list and return its head. Okay, so it looks like all it's asking us to do just from the problem, is that we are given the head of a linked list and it looks like here, okay, and wants us to remove the nth node from the end of the linked list. Okay, so from the end of the linked list. So we have the second node accordingly, and we remove that, and therefore we have 1, 2, 3, and 5. Same thing for, well, if we have 1 in particular, and we remove the first index, since we are removing from the end of the list, that's kind of tricky to start. We're then going to have 1 accordingly. So that's why in particular we have this input and the output. So from the end of the linked list, the output is a new linked list with the output, or hang on, with the nth node removed. So there we go, between our relationship. And so the technique to introduce you folks to that's going to help us solve our problem is going to be 2 pointers. We have 2 elements of data we will put at the head of the linked list, as well as a second pointer after the first pointer. And this will help us scan throughout the rest of our linked list, given the fact that we were just given the head, so we can remove our nth node. Okay, and the following steps in order to break down the following problem are as follows. So for step 1, we're going to initialize our 2 pointers at the head of the list. Then we will move the first pointer n nodes ahead from the end, and we will use a for loop to iterate through. And then if the first pointer is null, we return the next node of the head, and this means n is equal to the length of the list, and we need to remove the head node. And then we need to move both pointers until the first pointer reaches the end of our linked list from the n, and then we will make the next of the second pointer when n is removed to the next of the second pointer, which will remove the nth node from the end. So we scan it once, ultimately, then we scan it a second time to be able to remove our following linked list accordingly. Since we are given the head, our first pointer ultimately really starts from the beginning, scans through, and then our second pointer is going to scan backwards, since we already have our pointer, our first one already scanned accordingly, so we can then figure out exactly where to remove from the nth node. And then we'll just return our head once it's fully updated. So the way how to break down this following problem in the number of steps is that step 1, we'll have a list node represented first, which will be the head of our given linked list, since we're starting from the head. And then we'll have node and then we will have our second equal to the head just to initialize, and then we're going to iterate through throughout step 2 for int I is going to be 0, I is less than n, and I plus plus. Then first is going to be equal to the first next node while we are scanning through. And then step 3, if first is equal to null, we will have to return the head as an edge case for next. Then for step 4, while first is next and it doesn't equal null, in this case, we will set the first node to be the next of the first node after, so it will be after head, and then second will be second to next. Finally, step 5, we are going after the first node, scan through, then we are going to update our list with second, next, and next. Finally, returning the head of the new list. All right, putting it up here. Okay, let's just run this to double check. All right, passes all the test cases accordingly and submit. Okay, and just give a rundown and breakdown of our time and space complexity for the following. The time complexity is O of L, where L is representing the number of nodes in the list. And this is because we simply traverse the list in just one pass, while the space complexity, on the other hand, is O of 1, because we only use a constant amount of space to store our 2 pointers. And yeah, so this was remove nth node from end of list. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we are going to go over the blind 75 in C++, and today we are working with Reorder List. Now, to be able to give a breakdown of exactly how we need to solve for this problem, first we need to ask ourselves these 4 questions. What are inputs going to be? What data structure / algorithm / technique to use? What to do with the data? And finally, what our output is going to be. So now, just to give a breakdown on the problem, you are given the head of a singly linked list. Well, we already know exactly what our input is going to be. The list can be represented as following. We have this order, and now we need to reorder list in the following form. As indicated over here, symbols can be confusing, but again, it's going to be agnostic just based on the following formula that we would have. So it's saying you may not modify the values in the list nodes, only nodes themselves can be changed. Okay, so we need to focus on the nodes position. So we need to change the nodes position based on their desired order. And we need to return a modified length list. Alright, so the technique for us to be able to solve the following problem that we would need in order to rearrange the order is that we are going to be using a fast and slow pointer method. It's the tortoise and hare algorithm. Where we have a fast and slow pointer. And we focus on dividing the linked lists based on their halves, reverse one of the halves, then merge them together. So, the steps for us to be able to solve the following problem are as follows. Step 1, we're going to have the edge case where we have a null pointer. Step 2, we're going to initialize 2 pointers at the head of the list to find the middle. In step 3, we're going to move the first pointer 2 steps at a time, and the second pointer 1 step at a time. Then the next part, we're going to reverse the second half of the list. The fifth step, we're going to merge the two halves, taking one node from each half alternatively. Then we're going to initialize our two halves and expand upon the relationship between the first and second nodes. And finally, we're going to set the second node as the next node. So to give the following, what we're going to do in our following steps, I'm just going to move all this up here. So we have step 1, step 2, step 3, step 4, step 5. Is that in step 1, we're going to have the head, if head, null pointer, or head of next is going to equal the null pointer. We're going to return this. Then for step 2, what we will do is that we're going to initialize the 2 pointers to the head of the list to find the node. So it's going to look like this: list node, slow, head, and then also we'll have the same for fast. Hence the concept of hence the tortoise and hare type of method. And then what we will be doing is that we're going to move the first pointer 2 steps at a time, second pointer at least 1 step at a time. So that will be step 3, while fast and fast, move over next. We'll have slow equal to slow next, and then we'll have fast equal fast next of next, because the fast node is intended to be ahead of the slow node. And the fast will be the second half, and the slow will be the first half in order of reversal. Then we're going to reverse the second half of the list. So the way we do that is that we're going to have a list node for previous. That will indicate the first part. We're setting it to null. And then what we will do is that we are going to then have the same. Make sure you also capitalize your L's. We're going to set our current to slow, which is called up here. Then we are going to initialize our next node as well. And we do so by the following. And so what we will do is that we are going to have a while loop that's going to represent the current. Then we're going to have a next node redeclared as current for next. Then we'll have the current node next step equal to previous. And the reason being is because we're doing a swap in this case. So we'll have previous equal current, and then our current equal the next node. Then for step 5, we are going to merge the two halves, taking one node from each half alternately. So then we are going to have the list node for first equal to head. Then we're going to have the list node for the second one equal to previous as our. Once we divide it all up, then what we will do, and this is the initialization part, then this will be, we will expand upon the relationship. So we'll have while second is to next. We will then have the next node equal to first to the next. Then we're going to have the first next equal second. Then we'll have the first equal next node. as a swap indicated. Copy the first half, and then we're going to set the second node as the next node, which will be C. So next node equals second, next, second, next equal first, and we'll have second equal next node while we are looping through accordingly. Here we go. It's supposed to be in here. Just making sure every single bracket is counted. Let's take into account. Yep. So let's double check on everything. Misspelled here. Alright, passes all the test cases and submit. Okay, and so for a solution, just to give a breakdown on the time and space complexity for the following, is that the time complexity for our solution is going to be O of n, where n is the number of nodes in the linked list. And this is because we are essentially doing a single pass over the list, finding the middle, reversing the second half, and merging the two halves. Then for the space complexity, it is going to be O of 1, because we only use a constant amount of space to store our pointers. And yeah, so, and we're also not, and we're only using the linked list that we're also given at the same time for a given head, so that also gives the description for the space complexity as well. So yes, this was Reorder List. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe, and if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going over some Blind 75 C++ Leetcode, and today we are going over reverse linked list. So, just to give a rundown on everything over what we are doing. So we have a following linked list that we have where we're starting at the head, and then we are progressing our way to actually reverse the whole linked list. Again, it's a pretty simple operation over what we need to do, and before we get started, just sticking with the formula over what we need. We ask ourselves what the input is, what data structure / algorithm / technique to use, what to do with the data, and what our output's going to be. So the input that we have, we are given, just putting up our questions here, our answers down here, skip-a-dip-up input. So right here, we are given a linked list with a head node, hence right here. And then the data structure that we would need, or technique we have to use, we would use an iterator approach with 3 pointers to reverse the linked list. What to do with the data? We will modify pointers of each node to reverse the direction of the links, and then for output, we will return the new head of the reversed linked list. And so now this is just at the point of myself showing you how to do it, so we will then just go over the steps over what we need to do, which we'll break it down into 5 steps. So putting in this in our section 1, we need to initialize 3 pointers, which will be the previous, where we will initialize as null, because everything is connected. Current as head, and next as null, because we haven't seen anything yet. Alright, and we're going to loop through the linked list until current becomes null. Since we're moving up, we're treating this like an array. Third, we each iteration, we will assign next as the next node of current. So technically we kind of have 4 pointers to start. Change the next pointer of current to previous, and reversing the link, move prev to current and current to next. Finally, after the loop, we will assign the head as the new head, which is now the last node of the original linked list. So just to give a rundown, a linked list is pretty easy to understand. It's like an array, but instead it's connected. That's just the best way of describing it. And then finally, we would return the new head, which will have the rest of the elements slash nodes. All right. And it's highlighted right here. That's similar to step 5. Boom. Okay. So now I'm just going to go over a process, what we need to do. We're going to first initialize 3 pointers. I'm going to, as indicated, that next is going to be up here. That's what we need, and we're given a library of linked list. So list node prev is going to be null, and list node is going to be current, which is the head. List node is going to be next, which will be null. And we will go through, we will loop through our linked list until current becomes null. And that means while current is not null, with each iteration, we will assign next as the current. So next will be current with next, and change the next pointer to the previous. Or next pointer to the current to previous, reversing the linked list. We have current, next to previous. To move prev to current and current to next. Prev equals current. Current equals next. This is what we call a swap. But we're not using the STL library. We're just assigning the new pointers, and that's it. And then assign head to previous, because previous is current. Head equals prev. Make sure, and this is while we're doing this. And this is step 4. Assign the loop as the head of the new head, which is now the last node of the original linked list. Head is prev. And then finally, what we are going to do is then return our head. All right, passes all the test cases. And all right, it works. Okay, so just give a breakdown on everything that we have done. In fact, I'm just going to clean it up so you folks can actually understand what we're doing. I'm just going to move all the pseudocode in the steps right over here. All right, double checking. And it passes. Okay, so when reversing a linked list, which is like an array, except for it has literally other elements assigned to it, what we will be doing is that we will have a time complexity of O of n, which refers to the length of the linked list, and it's constant. And then we have a space complexity of O1, since we're not using a data structure to be able to store or keep track of anything. We're instead just scanning through the entire linked list. And yeah, so this was reversing a linked list on Leetcode. Thank you again for taking time to watch this. If you found this helpful, be sure to like and subscribe. And if you have any questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we are going to go over the blind 75 in C++, and today we are working with reverse bits. Now, before we get started, if you're following along, feel free to pause the video to write down our 4 questions and comments. For whenever we are answering these types of questions, we always ask ourselves these 4 questions. We need to ask ourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and finally what our output's going to be. So, again, feel free to pause the video if need be. So, when breaking down the question, what we need to do for the following is we need to reverse bits of a given 32 bits unsigned integer. Now, I'm going to have visuals up here to be able to help you folks be able to understand between different data types, because the technique we're going to be doing today is bit manipulation. And I'll also have some signs with some operators as well that we use for bit manipulation in order to solve the following problem. But what we will be doing is that if we have a 32-bit unsigned integer that we have, we just need to reverse that and finally have our numerical output at the same time. So, as indicated over here, and this requires the use of binary operators to be able to manipulate our following binary input. So, what we need to do is that we need to return the reversed bits. There's some notes on here about Java, but we're focusing on C++. What to do with the data, reverse the bits, and then input. We are given a 32 bits unsigned integer. And there is a key difference between signed and unsigned integers. In particular, I also have another visual to also further explain that will be up here. And without further ado, let's be able to write out the solution for this, because it's going to be pretty straightforward over exactly what we need to do. This will be taken in 3 steps. So step 1, what we need to do is that we need to initialize the result. And the second step we need to do is initialize a variable to keep track of the number of bits to be processed. In step 3, we need to reverse the bits of the given integer using a while loop. And for the first part of 3 inside the while loop, we're going to shift the result to the left by 1. And then we are going to shift the given integer to the right by 1. And then set the least significant bit of the result by bitwise OR operation with the least significant bit of the given integer. Finally, we will decrement the number of bits, since we all have 32. And finally, for step 4, we return the result. So, breaking down what we need: step 1, step 2, step 3, and then step 4. So, for step 1, it's going to look like this. We're going to have an unsigned integer, unsigned 32-bit integer called result. And then we're going to initialize a variable to keep track of the number of bits processed, given the fact that literally in the name 32 bits of an unsigned integer, we're just going to put the number of bits equal to 32. Then what we'll do is that while the number of bits is going to be greater than 0, since we have 32 bits to start, it's going to put down A, B, C, and D. First part for A, we're going to shift the result to the left by 1, indicating that we have already visited the following, since what we will be doing is that we're going to be scanning our entire following unsigned integer of 32 bits on the very far right side, and we're going to go down every single one and then output every single one in order. Like we see 0, 0, and then we also see 0, 0, and then 1, so on and so forth. So the first part, the way it's going to be done is that we're going to have result shift it over to the left, and I'm also going to have a visual for the bitewise operations as well. And then the next part, what I'm going to be doing is that I'm going to take a 32-bit operator, shifting it over to the right by 1, indicating that we have already visited, and so this is how our output's going to be done. And then we're shifting over to the right to build out our result. B is building out our result. And C, what we're going to do is that we're going to set our result that we made over here, a 32 unsigned integer, 32-bit unsigned integer, equal to the bit. And then we're going to decrease the number of bits, since we have already visited it. And it's going to go down. As we are scanning through, we're also outputting the reverse 32 bits integer. And finally, we are going to return our result. So 4 parts for 3 is that, just to give a rundown, we created a variable called result. Then we have the number of bits, 32. And while the number of bits are greater than 0, the result will be shifted to the left, since we are scanning from the very far right all the way down. And then we initialize a new bit type of integer. That will be our output. And while we are moving n all the way to the right, since we indicated n over here, that will be indicated as bit, we shifted it over more so to the right using our right operator, and then set it equal to our result, and finally decrement the number of bits to be able to finally have our output. So let me just run this. Alright, it passes all the test cases, and we are done. Okay, so just to give a rundown and breakdown of our space and time complexity for the following solution is that the time complexity of the solution is O of 1, because the number of bits processed is a fixed set of 32 bits, while the space complexity is also O of 1, since we are using a constant amount of additional space. And so, yes, this was Reverse Bits. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we are going to be going over the Blind 75 in C++, and today we are working on the problem rotate an image, or rotate image per se. So, before we get started, make sure that whenever we are breaking down our question, we have our 4 steps that we need to do. I'm just going to write them all out so that way you can follow along too. Let me just get this right here, copy paste here, here, and here. We need to figure out what the input is, what data structure / algorithm / technique to use, what to do with the data, and what our output is going to be. So, to be able to break down on the problem, you are given an n times n 2D matrix representing an image. We can just copy this and put it inside of our input. and you can even look up here in the parameters to be able to see exactly what's going to be inputted, is represented in an image. Rotate the image by 90 degrees, okay, clockwise. You have to rotate the image in place, which means you can modify the input 2D matrix directly. Do not allocate another 2D matrix and do the rotation. Okay, so that means we need to modify, and that means we're not going to be necessarily storing per se. Okay, we won't be storing anything, since right here, if we are rotating an image in place, we just need to modify the 2D matrix directly. And that means we're not going to make another matrix to store every single element that we are visiting. This part can be tricky at first, but if you understand more about data structures and algorithms, data structures can be used in particular to keep track of every single element that we have visited in order for our output, which would be our answer. However, we are not going to be using a data structure in this case. Instead, we are just going to be doing this technique called an in-place matrix rotation. And what is that really? Well, an in-place matrix rotation is really just two for loops where we swap both of the first element we scan and the second element we also scan as well. So, for instance, if we were to have a matrix of 1, 2, 3, 4, 5, 6, 7, 8, 9, what we need to do really, in terms of rotating it, you notice the numbers 1, 2, and 3, they're all going to be rotated 90 degrees. So 1, 2, and 3 accordingly. And then also the same thing 4, 5, 6, which would therefore be 4, 5, and 6, 7, 8, 9. Accordingly, it would just be rotated in the rows and columns accordingly. One could even take apart the matrix as well to be able to fully understand, but we're just rotating 90 degrees accordingly. So that means we are going to be scanning the entire matrix. And since we are going to be calling upon this method called swap, both I and j respectively, one end to another. Okay, and so the steps for us to be able to do is that first thing we are going to do, there are some great tools in the STL library. We are going to be first reversing the matrix from beginning to end. Then the second step that we will be doing is that we are going to be swapping the elements across each diagonal of the matrix. And for each row, then what we'll be doing is then swapping the elements which have been reversed. So we're going to be focusing on these three steps accordingly. So the first step we are going to be doing is that we're going to be calling on reverse from the STL library. Reverse matrix begin matrix dot end. Step 2, we're going to be swapping the elements accordingly. So we're going to have two for loops as indicated by our technique, we're doing an in-place matrix rotation. So it's going to be int I is going to be 0, I is going to be matrix, and it's going to be less than matrix dot size I plus plus. And then we're also going to have a second for loop accordingly as we are scanning the entire matrix again, but from the next element as well. 1, j is going to be less than matrix. We are currently at, since we need to take into consideration if we have 2 elements right here. Size j plus plus. And then we are going to be swapping our matrix from I and j, and matrix j and I accordingly. And actually, this is a very, very simple type of solution at the same time, because we have already rotated our matrix accordingly. I know this may be a little bit confusing to be able to start, but this is just the techniques that we have already been taking in from the STL library, where we are taking one element that we have already have, and then we are going to be swapping it accordingly after we have reversed our following matrix. And then once we have reversed our following matrix, we're then going to be swapping each of the elements within a 90-degree plane. So let's just see if this runs accordingly. And Leetcode is down. That's kind of cool. Yeah, that's absolutely great. This entire website is completely down. So anyway, just to be able to go over the space and time complexity for our following solution, I'm also going to have it up here and be able to edit it, is that given the fact that we have 2 nested for loops accordingly, the time complexity for this is going to be O(n) squared, where n is the number of rows relative to the matrix, since we're also scanning both 2 elements accordingly. And then we're going to have a space complexity, luckily, since we are not using any data structure to store anything. The space complexity is going to be O of 1 to start with, since we're not storing anything and we are asked to be able to rotate the matrix as is. So yeah, this was Rotate an Image. Thanks again for taking time to watch this. If you enjoyed this, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. As always, take care. Cheers. Hello everyone, today we're going to be going over some Blind 75 C++, and today we're working on the problem same tree. Now before we break down and go over our question, we need to ask ourselves the for question, what are inputs going to be? I'm going to just copy and paste for the rest, you can follow along too. What data structure / algorithm / technique to use, what to do with the data, and then finally what our output is going to be. So to be able to break down the following problem, what we have is that we were given the roots of 2 binary trees, P and Q. Okay. Trees, P and Q, especially specified by the parameters up here. Write a function to check if they are the same or not. All right. And what to do with the data, we are checking to see if they are the same or not. And then we will be returning true if the same. So the technique we will be doing is depth first search, namely, to be able to make a comparison between the two, where depth first search pretty works and is really extensive, given its space and time complexity that we would use and keep everything within the constant space. And so what we will be doing is that we're going to be checking on the different values between all of our null, all between our pointers, between if one of P or Q is null, or the values are not equal to each other. We're going to be having one condition where it's going to be false, and then we're going to see in particular if P or Q are going to be matching up. So use this technique to check their pointers first, and then we also do a recursive call to check to see the left and right subtrees of P and Q just from the roots. For depth first search is known for recursion. So to be able to break down the steps or what we are going to do, step 1, we are going to we're going to be checking if P and Q are null, return true. And then for the second part, if one of P or Q is null, or their values are not equal, return false. And then we're going to be recursively calling the function for the left subtrees of P and Q. And then we will be doing the same thing, but for the left subtree. So we're doing this for the left and the right accordingly, and then we will be returning the results of the recursive calls for both the left and right subtrees. Okay, so here we go. So to be able to break down the whole problem, or what we will be doing, we're going to be focusing our null pointers to be able to initialize steps 1 and 2. So if P, the root, is a null pointer, and Q is also a null pointer, we're going to be returning true in this case. And then if one of P or Q is null, they are not equal. So if P equals null pointer, or Q is equal null pointer, for we're not doing this and up here, and condition, or P value does not equal Q's value, we're going to be returning false. So then we cover that. Now we are going to be doing our recursive call with DFS. DFS recursion. So we're going to have one function, boolean is left, same is same tree for the left side, Q left. This is typically called within the STL library for the following. Tree that we're also calling is right same. We're having this boolean is same tree, where we're calling upon this function right over here, our boolean condition, to be able to check for the subtree as well. So then we are going to be setting the left subtree that we have inside of our function right over here. So this will be a form of recursion. So P to the right, and then Q to the right subtree. There we go. And our output, return the conditions of both the left and right subtrees. Since we've already took care of our nodes of our given tree, now we're focusing on the subtrees. Since it's very easy to figure out between the first two, we're going to be focusing on the nodes of the tree, or the root slash head of the tree. So then we'll return is left same and is right same, because both of them need to match up accordingly. We're checking for every single value that we can find, and we are setting P, the parameter, to our left, and then Q to our left as well. We're checking them all together and doing this recursive call that is made accordingly. And we are already given the values of left and right in our tree structure that we can call from the STL library. So let's just double check to see if this is all right. So it's accepted. Okay, let me just clean all this up for you folks. This is step 1, and this is also step 2 right here. And then subtrees. It's all accepted. Just want to be sure I get everything right. And we'll submit this. Okay, and just to give a breakdown on everything that we've done. So the time complexity for our following solution is going to be O of n, given the fact that n represents the number of nodes within the tree. And the space complexity for the following is going to be O of h, where h represents the height of the tree. So therefore, it would all run within constant space. And we do this by using depth first search to be able to make recursive calls for our following solution right over here. So yeah, this was same tree in C++. Thanks again for taking time to watch this. If you found this helpful, like and subscribe. And if you have any other questions, feel free to put them in the comment section. As always, take care. Cheers. Bye-bye. Hello everyone. Today we are going to go over the blind 75 in C++. And today we are working with the problem serialize and deserialize binary tree. So before we get started, now, mind you, what we will be doing is that we're going to be filling in these two types of functions for serialize and deserialize. So I'm going to provide just the steps that we need for each function accordingly. And then, without further ado, let me just put them over here. So, to break down the question, serialization is a process of converting a data structure or object into a sequence of bits so that it can be stored in a file or memory buffer, or transmitted across a network connection linked to be reconstructed later in the same or another computer environment. Design an algorithm to serialize and deserialize a binary tree. There is no restriction on how your serialization/deserialization algorithm should work. You just need to ensure that a binary tree can be serialized to a string, and this string can be deserialized to the original tree structure. Clarification also, the input/output format is the same as how Leetcode serializes a binary tree. You do not necessarily need to follow this format, so please be creative and come up with a different approach yourself. Okay, so for what we will be doing for our following steps is that, for one, we are given the root of a binary tree as our input. So I'm just going to label out the rest of our following questions over what we need to do, so we know exactly what our input is. The root of the binary tree. What data structure/algorithm/technique to use. What to do with the data, and finally, what our output is going to be. So we're given the root of the binary tree. It looks like from our input to output, our output for serialization, we need a string that encodes the structure of the tree. For deserialization, the root node of the reconstructed tree. So then the technique that we're going to be doing for this, since we're focusing connectivity of a given tree, is that we're going to do depth first search using recursion for both serialization and deserialization. And so the steps for us to be able to go about for each one are going to be the following. Over here, for two functions. I'm going to put these notes in the comments as well. Is that for serialization, we will overall
we will traverse the tree in pre-order traversal and build a string representation using essential value for null nodes. For deserialization, we use the pre-order string representation to reconstruct the tree, creating new nodes for each value and null for the sentinel value. So the steps for us to be able to work with serialization are going to be the following. If the node is null, we will return a sentinel value. Otherwise, we will return the string representation of the node value followed by the serialized strings of the left and right subtrees. And then for deserialization, we will split the string by the delimiter to get a list of node values and create a helper function that if the current node value is the sentinel value, return null. Otherwise, create a new node with the current node value. Then recursively build the left and right subtrees and assign them to the node. So, going over serialization, what we will need to do is that if we are at the root, for instance, and the null, and we are at null, what we will do is that we are going to return actually this value, which is going to be represented in the sentinel value. So it's just going to be the character of x with the space, and then we're going to return the string representation of this. So this will be step 2. Return to string root val plus serialize the root to the left and serialize, literally doing recursive calls, to the right. All right. And then to deserialize, we're going to do the following. Step 1, step 2. Is that we will have string stream in data, and then we will return a function that we create, my deserialize value in, which will be referring for over here. This will be step 2, and we're going to create a function that we will call. Using a helper function. So the helper function that we will have will look like this. since we're working with the tree node, I'm going to deal with this helper function for deserialization, and there we go. That's for us to be able to create our helper function for deserialization, transferring the data from one format to another. Since we're transferring from a tree all the way to a string, the helper function is going to have the following steps. Is that if the current node value is the sentinel value, return null, and then otherwise create a new node with the current node value, then recursively build the left and right subtrees and assign them to the node. So the way we're going to have them about is going to be this. So step 1, step 2, if val is equal to x, we are going to return a null pointer, much like what we did above. And we will create a new node, tree node, root equals new tree node, stoy val, and we'll take the left with a recursive call, with what value we have with a given node. Make sure they have their semicolons. Finally, we return the root. So let me just run this. Oh, we have an error. Okay. To initialize what we need up here, is a string called value, and make our data of n the value we will evaluate. So that means in particular for entirely of step 1, we have 2 and 3, and I'm going to have all the corrected ones in the description. String val in val. There we go. That should work. Stand corrected. Make sure there's a space. There we go. Passes all the test cases. Let's submit. All right. Now let me just expand this further. Just gonna move this up for you folks. There we go. Now seeing the whole solution that we will have. So to give a breakdown on our space and time complexity for our following solution is that the time complexity is going to be O of n, given the fact that we are traversing a binary tree using depth first search, since each node is visited at least once. Meanwhile, the space complexity of our solution is going to be O of n, given the fact that n is referring to the size of a serialized string when returned, and that's really just the scope of what we are doing, because we need to convert our given string data all the way back to a tree. So yeah, this was Serialize and Deserialize a binary tree. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put in the comment section. And as always, take care. Cheers. Bye-bye.
Hello everyone, today we're going to be going over the Blind 75 in C++, and today we are working on the problem set matrix zeros. But before we get started, make sure that we always break up the following question in our formulation. We need to figure out what the input is, what is our expected output, and what data structure / algorithm / technique to use, and what to do with the data. Alright, so just to give a rundown on everything else so that way we fully understand the question, let me just get all these comments set up in place. You can follow along too, side by side. So, given a breakdown of the question, given an m times n integer matrix, if an element is 0, set its entire row and column to 0. So, it's pretty self-explanatory over what we have. So if we find a 0 within our given example that we have of our matrix, we are going to set all the rows and the columns accordingly to 0 of everything that it touches. Okay. We are going to set all of the touching elements which are associated with 0 in the input to 0 for our output. That's pretty self-explanatory from the first example and the second example accordingly. And so what we will be doing is that we will be introducing a technique called iteration, where if a 0 is found, we are going to set the first cell of that row and column to 0. Then we are going to iterate again if the first cell of a row or column is 0. We set the entire row or column to 0. Accordingly. So that means we're going to be looping throughout the rest of our given rest of our given matrix that we will have. Right here. Let's put the notes down here. Zero right here. Okay, and given info that we have a matrix, and we are supposed to return a matrix with corresponding zeros. So, what we will be doing is that for a following way, we are going to first 2D matrix. So the steps we are going to be doing to be able to get through all of this is that for the first step, if a 0 is found at cell, let's just say for example cell I and cell I of j as our initial one, we're going to set the matrix accordingly, this one, and matrix 0 j to 0 accordingly. Step 2, we're going to iterate over the matrix again
to indicate we have a modification in place if matrix I of 0 or matrix, whenever we have a row or a column, is 0, we're going to set matrix I and j to 0. Then in step 3, we're going to be outputting the modified matrix. And so I'm going to be expanding upon the pseudocode to be able to help break down over what we need to do. So what we will be doing in this case is that for each cell in the matrix, for step 1, if the cell value is 0, we're going to set the first cell of the corresponding row and column to 0. And then what we'll be doing for step 2 is that we're going to be doing the same thing we did for step 1, except we're going to be iterating over again. So for each cell in the matrix, if the first cell of the corresponding row or column is 0, we're going to be setting the cell value to 0. And again, step 3 is very self-explanatory. We will be outputting our modified matrix accordingly. So to be able to give everything that is already set in place, what we need to do for our very first step is that we are going to initialize everything to begin with for our matrix, assuming that we have not visited it. So first initialize our matrix to start. And step 1, we're going to initialize our matrix and assume we have not visited any row or column yet, which is 0. Then step 2, we're going to set accordingly. Step 3, we're going to do the same, and then step 4. So these would be 4 simple steps that we would have initially. So step 1, we're going to first initialize our matrix and assume that we have not visited anything yet. So we'll have M representing the relative matrix dot size we have, which is a technique in C++, int n, which is matrix row dot size accordingly, and then we are going to have 2 Boolean conditions to see if it is 0 or not. So first row 0, we're going to first consider it false because we haven't visited anything yet, and the first column of 0 is going to be false since we haven't visited anything yet. Now we're going to focus on step 2 accordingly that we have up here. If we found 0 cell I and j, which is a first indication in step, so that means we're going to have 2 for loops accordingly, one for I and one for j. Int I is going to be 0, I is going to be less than m accordingly, which would be the size that we have already initialized up here. Just for the sake of clarity, you can always use matrix.size. Doesn't really matter between them as long as you're able to get the solution right. And then we're also going to be iterating over j that will also represent the column. So int j is going to be 0. J is going to be less than the relative size accordingly I j plus plus. All right, here we go. And now we're going to have our if statement over here. If the cell value is 0, okay, if matrix I and j are going to be equal to 0, then what we're going to be doing is that we're going to be set matrix I for the row, j for the column, matrix 0 and j
accordingly will be 0 to start. And then if I is going to be equal to 0, we have indicated that the first row 0 is considered going to be 0 accordingly, which will therefore be true. Same thing for j as well. There we go. First call 0, first call 0. Yes, indeed, we got that. Let's see if we are moving forward. And now we're going to iterate over again, except for the key difference between the two is that we are going to have a different type of element that we have already visited. That's not going to be the very first one. So zero accordingly. This is why we do this. So I can basically do this entire for loop again for the sake of clarity, except we're going to replace this as 1 and also this one as 1, 2, because we're iterating over the array again accordingly, except for this time we are going to be checking to see if a row or column is going to be equal to 0, and then we're going to set everything to 0. So this is going to be our modification. If matrix I row is equal to 0, or this represents the row, and we're going to have the same for the columns, 0 and j accordingly for the row and the column. So this would be for the column, this would be for the row, since I is the row, j is the column. Accordingly, yes, and then we're going to set everything to 0. So matrix I and j is going to be 0 accordingly. Now we're going to have our edge cases over here. If now this will be the case where if it is true, so if first row 0 is true, we are going to be going over the entire column accordingly. J S n, which would be j plus plus matrix. That's because we're going to set our row to 0, and then j accordingly will be that. And now we'll do the same for the columns, converting rows to 0, converting columns to 0. First row 0, first call 0, I 0, I M I. Yep. And since we are, this will be our output that we would have accordingly. Output is right here. This can also be indicated as our output 2, but here, this one as well. Right here. There we go. So let's check to see if everything runs accordingly. Make sure that we don't have any syntax errors to start with. Still going through. It passes all the test cases. And we will submit this one. Okay, and all checks out. Now I'm going to clean this up for you folks so that way you folks can actually understand and fully see the problem. So let me just go back. I'll clean all this up for you. Alright, so this is our following solution. Actually, I'll clean this up even more. All right, so this is our following solution that we have over here. So to give a rundown and breakdown of our time and space complexity for our following solution is, given the fact that we have a series of rows and columns and we're keeping track of everything that has already been visited to start, making a series of Boolean conditions, our time complexity is going to be relative to the number of rows and columns accordingly. So therefore, our time complexity is going to be O of m times n. However, the good news is we're not using a data structure to store anything that has already been tracked. We are only scanning through the rest of the matrix. So therefore, our space complexity is going to be very efficient for this, which is going to be O of 1, which will therefore be linear and not constant, since we're not using any extra space to be able to store anything that we have already set in place. And people can solve this problem with a map or a set accordingly to store everything. However, within the efficiency of our space complexity, this is why we're just scanning throughout the rest of the array to be able to have a set solution. All right, so this was set matrix zeros. Thanks again for taking time to watch this. If you enjoyed this, feel free to like and subscribe. And if you have any comments, feel free to put them in the comment section. As always, take care. Cheers. Bye-bye. Hello everyone, today we are going to be going over the blind 75 in C++, and today we are working on the problem spiral matrix. Now, prior to breaking down the whole entire question, we need to ask ourselves our 4 questions: what the input is going to be, what data structure / algorithm / technique to use, what to do with the data, and then what our output is going to be. So, to go over the problem, given an m times n matrix, return all the elements of the matrix in a spiral order. Okay, we can even look at the parameters at the same time to be able to know what we're inputting. We are given a matrix, and it looks like when we go over the example, we have a given matrix, but then it looks like, well, the matrix is indicated by the commas over here. The output is going to be indicated by this list we have. So it looks like we are going to be returning a list, and it looks like, for instance, if we have a matrix where the elements are in order per se, we are going to have an output. It looks like the elements are within a spiral order accordingly. Okay. And so the technique I'm going to introduce you folks to is going to be called an iterative approach, where we have 4 pointers. And we will use them to print out each of the directions of the 4 pointers. So this may be a little bit confusing at first, but I'm going to be explaining more within the steps that we have. And so we will have, in order for us to be able to replicate this entire behavior of the iterative approach, what we need to do is that first we need to define our 4 pointers: top, bottom, left, and right. We also initialize list, which will be a vector, since naturally arrays and lists can be treated as vectors and such. And so the next step what we will do is that we are going to run a while loop from loop until the top of the matrix is less than or equal to the bottom, and the left of the matrix is going to be less than or equal to the right. And what we're going to do is that we're going to print the top row from left to right, and then increment the top pointer. And then we will print the right column from top to bottom, decrementing the pointer, right pointer. And then we will be reaching to this point. If the top is less than or equal to the bottom, we're going to print the bottom row from right to left, and then decrement the bottom pointer. And then if the left pointer is less than or equal to the right pointer, we're going to print
the left column from bottom to top and increment the left pointer. And finally, we're going to be returning our list of elements. Technically, it's 8 steps accordingly. So, to be able to break down everything that we will be going over, we're going to be doing step 1 and 2, where we will first top is going to be 0, and then int bottom is going to be equal to the matrix dot size. For the very last element over here, int left is going to be 0, int right is going to be equal to the matrix, the very rightmost element, size, less 1. Then we're going to have our list that we initialize, which will be a vector, and then we return the result. Then we're going to do step 3, which we are going to be doing a while loop to expand upon our relationship. Top is going to be less or equal to the bottom, and left is going to be less or equal to the right. Accordingly, then we're going to replicate our behavior for our 4 pointers with what we were doing through steps 4 through 8, or 4 through 7. Results list. So steps 4 through 7, we are expanding upon our 4 pointers and put them in our results list. So what we will be doing, step 4 is going to be left to right. So 4 int is going to be starting to the left. And then I is going to be less than or equal to the right. I is going to be incremented. And then what we'll be doing is that result push back matrix at the top. I'm going to increment our top accordingly. And then step 5 is going to be top to bottom. So we will do this part. It's going to be the same thing over here, where I is going to be the top and it's going to be the bottom accordingly. And then we're going to do this from the right. Right pointer. Select. Okay. And then we're going to do step 6, where if the top is less than or equal to the bottom, what we're going to do next is then we're going to be int I is going to be the right, I is greater than or equal to the left. We're going to decrement I accordingly as the inverse relationship, and then we will matrix of the bottom of I, much like in the case of the top we have over here, and then we will be decrementing our bottom. Then we're going to do step 7, which is going to be the opposite relationship with this one over here. So it's going to be having the same if condition, except for it's going to be the left. It's going to be less than or equal to the right, and then we have I is going to be the bottom. I is greater than or equal to the top, and then we're going to decrement accordingly, and except I is going to be the left side. So expand upon set relationship as well, and expand upon their inverse relationship. Okay, right here. Finally, we will be returning our result. Because we have visited all of our following matrices accordingly, this will be step 8. Let's just check to see if it runs accordingly. wait, before, let's make sure that we have our syntax already set in place. Yep, okay. Looks good so far, but I'll also further correct if we ever need anything else. All right, it passes all the test cases, submitting this problem. All right, and it works pretty efficiently. Now let me just go back and be able to clean this up for you folks. On this accordingly. Yep. Okay, and submit. Woohoo, we got this. So, to be able to expand upon the relationship of the space and time complexity. So, our time complexity, given the fact that we are dealing with a matrix to even start with, and we are storing our following matrix within a list, the time complexity for the following is going to be constant, but instead it's relative to the rows and the columns, so therefore it's going to be O of m times n, where m is the number of rows and n is the number of columns. That's because every element in the matrix is visited once, and the space complexity is also the same, O of m times n, where m is the number of rows and n is the number of columns, because we are storing each of the elements of the matrix in a list to start with. So yeah, and the following solution is already further optimized since each element in the matrix is visited exactly once. And yeah, this was a Spiral Matrix. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comments section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we are going over some Blind 75 in C++, and today we're working with subtree of another subtree. Now before we get started, make sure that we have all of our 4 questions that we have laid out to be able to make sure that we know how to solve the problem by breaking it down. We need to first ask ourselves what the input is going to be, what data structure / algorithm / technique to use, what to do with the data, then what our output is going to be. So, just to break down on the problem, given the roots of 2 binary trees, root and subroot, that's already self-explanatory. We answer the first question, and you can also look at the parameters. What we have tree node 1, tree node 2, 2 roots of 2 binary trees, root and subroot. Return true if there is a subtree of a root with the same structure, and node values of subroot and false otherwise. Alright, so we already know what our output is. A subtree of a binary tree is the tree that consists of a node in a tree and all of the node's descendants. The tree could also be considered a subtree of itself. Alright, so that would be just one edge case to further consider as well. The tree could also be considered a subtree of itself. And so what we will be doing next is then just going over the example that we have. So it looks like that we have, so if we have the root of one binary tree and then the root of a subtree accordingly, of a subroot and then a root, we're checking to see if these values are matching. So that's all we are doing. Values from the subroot are matching any of the subtrees from the root of the binary tree. It's pretty self-explanatory, and then we return true or false, just seeing if these nodes accordingly within the root of our binary tree have the same values as the following right over here. So just to be able to break down even further, the technique that we will be able to use to be able to solve this problem is that we're going to be doing a recursive approach to check if one tree is a subtree of another. And what we will be doing with our data, aside from checking, we will traverse the trees recursively, comparing the nodes and their subtrees.
So then what we will be doing next, I'm just going to be going over the steps of how we will be solving this problem. And let's just double check for case of that. Yep, it's pretty self-explanatory between examples 1 and 2. Check and see if these subtrees have accordingly the same type of numbers already between the subtree as well as the binary tree. Now this example may have the subroot values, but then we have this 0 at the end that will also expand upon 2. So if we were to break down how a binary tree works for the most part, it typically would start with the root, then you go left, then you go right. Then what we will do is that from the left side you go left and then right accordingly, and then so on and so forth. So if you have right, then you do the left of the right, and then right of the right, and so on and so forth. That's just the general pattern that we would have, such as 3, left, right, and then we will have left of left, left, right, no, yep, this indicates for 5 accordingly, and 1 as well. So that's why we have this null, this is for 5, this is for 1, but then we have 0 over here for 2, which would be right over here. It's left to left. And this will not work because of this 0 that we have. So self-explanatory. Now just to go over the steps, first thing that we will be doing is that we will check if T is a subtree of S by calling a recursive function is subtree. S and T, define a recursive function is subtree. S and T to check if T is a subtree of S. If either S or T is null, will return true if both are null, indicating an empty subtree, or return false otherwise. And then we're going to check if the current nodes of S and T are equal. If they are equal, call the isSameTree function to check if the remaining subtrees are identical. If the subtrees are identical, return true. If the subtrees are not identical, we're going to continue searching for T as a subtree in the left and right children of S, and then we'll return the logical OR of the results obtained from the left and right subtrees. Next thing we will do is that we will define a helper function is same tree, which are P and Q, to check between if two trees, given hypothetically, P and Q are identical. If both trees are null, return true. Then if either tree is null, or the values of the current nodes differ, return false. Then we're going to recursively check if the left and right subtrees of both trees are identical. We're going to return the logical and of the results obtained from the left and right subtrees. Ultimately, just having the then we're just going to return the result of the calling of calling the isSubtree function on the given trees. So now just to be able to write out the code for each of the steps that we would have, we're given the input. Now what we will do is that we're going to do something pretty unique. So we are going to do a recursive call, as stated before, isSubtree st. Then we're going to use this part to be able to make our recursive calls. So we're going to create two.
You can probably put them in private as well.
Excuse me. So I'm going to create this first recursive call function of boolean is subtree helper tree node s, and then tree node t. Make sure it's all spelled correctly. Then we will do yes. If s equals null pointer and t equals null pointer, we're going to return true. Given the fact that they're both the same, that's our first edge case that we will deal with. Since they have to be the same, if s equals null pointer or t is equal to null pointer, given the fact that they're different, we're going to return false. Now that we got those, checking. All right, step 4, checking to see if they're equal. If s val equals t val, and this is the part where we're going to be creating our isSameTree type of function. So that means that this will be step 5 accordingly, and if isSameTree, we'll construct more of the other function that we will create, and then Alright, step 6, we're going to return true, given the fact that we have determined that they are the same. And then step 7, if the subtrees are not identical, continue searching for t, which means that will be returned is subtree helper, s for the left side, and t or is subtree helper. On the right side, t. And now for the next part, we are going to be doing this next function. Boolean is SameTree for 2 hypothetical ones, just for the sake of the parameters. So this is why we do this. P and then tree node Q. And then we'll be doing step 9 all the way through. Let's go, or this is step 7. Step 8. Step 9. Step 10 will be if p is equal to null pointer and q is equal to null pointer. We're going to return true, given the fact that we have found out that they are similar. Then, for the next part, step 11, where this will be false. Pointer, or q is equal to null pointer, or the value of p does not equal q's value, then we're going to return false. And then what we will be doing is that we will be doing a recursive call. So step 12/13. Again, similar pattern that we have done already before. We're going to recursively check and then do the logical AND operator. So that means it's going to look like a return is same tree, P's value on the left, Q on the right, and P on the right, Q on the left. And for step 14, return the result of calling is subtree function on the given trees, which is also the same as step 14. So let's just double check on this whole thing. Let me just make sure all the syntax is correct. I'm going to move all this up and just put this in the comment section to be able to help you folks see the whole solution and walk through each step. Okay, let me just run, and if there's any syntax errors, I apologize in advance. Okay, there is a syntax error that we have. Let me just double check to see what it is. Okay, so actually, this error that I have is supposed to be on the direct left, and then we have right as well. Unlike that, okay, so the logic that I was supposed to have is not left and right. It's supposed to be on the values of the tree on the left side that we compare, since we have two different trees, as well as on the right. So this explains why we're getting this wrong error. All right, it passes all the test cases. I'm going to submit. And it works pretty well. Okay, so just to give a breakdown on a space and time complexity for our following solution. The time complexity for our solution is going to be O of m times n, where m and n are referring to the number of nodes in the trees S and T, respectively. And then in a worst case scenario, we may need to compare every node in S with every node in T. While the space complexity for our solution is going to be O of max of m and n, where m and n are the heights of the trees S and T, respectively. And the space is using a series of recursive calls to represent the maximum depth of the recursion stack that we have. Hence, it would be constant, but since we are using two types of trees, we have the subtree as well as the binary tree, this is why we have them multiplied, as well as just figuring out the exact max between them when talking about the time and space complexity. And yeah, this was Subtree of another Subtree. Thanks again for taking time to watch this. If you found this helpful, like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we're going to go over the blank 75 in C++, and today we're working with sum of two integers. Now, before we get started, as always, we always need to ask ourselves these four questions: what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and finally what our output is going to be. So, going over the question, given two integers, a and b, return the sum of the two integers using the operators. Okay. And given the fact that we are doing a bitwise manipulation problem, we are going to do bitwise manipulation. And so what we are going to do with the data, with our given input, two integers, a and b. Now, this isn't the I understand by what you mean. Oh yeah, we'll just return the sum of integer a, integer b accordingly. But if we were to do that, int sum is equal to 0, and then we initiated, for instance, a plus b, and then return sum. This is not what they're going to look for. Watch this. Actually, never mind. This actually works. Strangely enough, we can do that. Just kidding, I wish. Just a little humor to help you guys out during the whole time. But anyway, I'm just going to give you guys the steps over exactly what to do on this whole thing. So steps to be able to go through on this. So step 1, what we need to do is that we need to initialize our 2 integers, and then we also need to initialize an unsigned integer. We're going to call this one carry. Then the third step of what we're going to do is that we are going to perform bitwise operations to calculate the sum. Step 4 is that while one of the numbers can be a or b, that we initialized doesn't equal 0. We calculate the sum by using the carry XOR binary operator. Then what we will do is that we're going to calculate the carry by using AND operator with left shifting. Next part, we're going to set the first integer to be the sum. Then we will set the second integer to be the carry. And finally, we will return the first integer. So to be able to go over the steps of what to do. So step 1, step 2, step 3, step 4, step 5 on what to do. Step 1, we're going to initialize everything along with step 2 at the same time. So int num of 1 is going to be equal to a, just for clarity. Int num of 2 is going to be equal to b for clarity. Of 2, we're going to create an unsigned int called carry that we initialize as 0 to start with, and then we're going to perform bitwise operation to calculate the sum, where that's just going to be step 4 ultimately inside. In fact, just for clarity, I'm just going to make this entire thing 3, and then this one 4. So right here, so while we can pick either 2, but I prefer to stick with num2 doesn't equal 0, then what we will do for a, b, c, and d is that we are going to calculate the sum, which will be num of 1 root num of 2. And then what we'll do is that we're going to set carry equal to static cast unsigned int of num1 and num2, shifting it over to the left. Then for the next part, for C, we're going to have num1 equal to sum, and then num2 is equal to static cast int for the carry. And finally, we will return our num1. So you can do the same thing, just keep it in order and such. So let's just run this to be sure this all flows together. And make sure that you have all your semicolons set up in place. All right, it passes all the test cases. Let me submit on this. And we have our solution. Let me just make sure the steps are already in line. Okay, so just to be able to give a rundown on our space and time complexity for our following solution. But prior to that, I want to showcase an example of a code walkthrough to be able to help explain exactly the step-by-step process to showcase our solution. All right, so just to go over an example of our following solution that we have, if say for instance that we are inside of this main execution that we have over here, and if we were to have the values where 0 is equal to A and 1 is equal to B accordingly, and we're going to have each of these numbers following update. So we already know for a fact that with int A and int B, from what we got below, 0 and 1, we're going to keep moving. As you see, they update accordingly. Still going again between num2, B, and then we're going to have an unsigned int carry that we initialize. After I press next, it's going to appear. And then while in this loop, since we have num2 equal to 1, since it is B, what we're going to do is that we're going to add up the binary between 0 and 1 accordingly. Then, as we keep moving, it's still updating. Okay, we've updated our sum, which should be 1. Then we're going to have our carry really take in the binary sum that we already got, and it's going to transfer it to become an integer where it looks like it's just 0 when it's coming out. Then we update the following, and we make our sum num1 trying to return num1. Then we just keep going until we have num2 being 0. When it's 0, we finally return the sum total that we made for num1, where it should be 1 accordingly. And that's what we do. The sum is 1. We're actually going to have a space and time complexity of our solution being O of 1. And also O of 1 simultaneously, since 1, we're not using a data structure to store necessarily everything. We're only using variables to be able to scan through our numbers in particular. And since we're only just checking the bits of the following integers at the same time, and we're just using a constant amount of space. So therefore, both our space and time complexity is going to be O of 1. And so yes, this was a sum of 2 integers. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone. Today we're going to go over the blind 75 in C++, and today we're working with the problem top k frequent elements. Now, before we get started, feel free to pause the video. For whenever we are breaking down these questions, we always need to ask ourselves the 4 questions: what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and what our output is going to be. Feel free to pause the video for a moment to be able to write out all these questions if you're following along. I just have them already set up right here. Again, feel free to pause. We need to ask ourselves all these 4 questions. All right, and now in order to break down our question, given an integer array nums and an integer k, return the k most frequent elements. You may return the answer in any order. Well, we already know exactly what our input's going to be. It's going to be this, and it looks like we need to return the k most frequent elements. Pretty self-explanatory. We solved 2 of our questions. Now let's look at the example to be able to understand exactly what we were working with. So if we have a given array of nums and the k most frequent elements, it looks like it's just asking us to return the 2 most frequent elements. So we have 1, 2, 3 ones. We have 3 ones accordingly. Then we have, it looks like, 2 2s and just 1 3. So there are 3 1s and 2 2s. The 2 most frequent elements are Yes, 1 and 2. And it looks like that we need to return this in an array, as they are expected. And it looks like this edge case, if it's just 1 and the one most frequent element, it will just be 1. Also some more constraints as well. Okay, it's the range 1, the number of unique elements in the array, so it starts at 1. And follow up, your algorithm's time complexity must run better than O n log n, where n is the array's size. Okay, so that's also another thing to take into consideration. And then the data structure and technique that I will be introducing your folks to is really just going to be a hash map with a priority queue. And to explain the data structures between the two over exactly how we're using them is that a hash map is much like in the case of a series of lockers that one would have. If one has a key that needs to connect to a specific locker, the value, you have a key value pair to be able to open your locker, and that is how the hash map is typically designed. And then the priority queue, for the most part, is that queues in general are much like in the case of grocery store lines, where it's going to be last in, first out on like a stack, where a stack is typically like a stack of plates, and it will be first in, first out. So that's just one thing to keep in mind, just for the visualization for the two, just by principle. And so to be able to go over the steps of how we're going to solve this problem step by step, is that first we're going to initialize a hash map to count the frequency of elements available. And then 2, we're going to create a min heap to keep track of the top k frequent elements. Our min heap is really just a priority queue. And then we are going to initialize the variable for the result. Step 4, we are going to loop through the array and count the frequency of each element using the hash map. Then for step 5, we are going to loop through the hash map and add each element frequency pair to the min heap. If the size of the heap becomes greater than k, we're going to remove the top, the smallest element from the heap, hence a priority queue. And then we will also pop out I was going to pop all the elements from the heap and add them to our result, ultimately returning our result. So to kick things off, for step 1, what we are going to be doing is initialize a hash map to count the frequency of the elements. So this is how it's done. Unordered map int, and then a count. And now, for the next part, what we'll be doing, in order to count the frequency of the elements, we're going to be doing a for each loop for int num of nums that we get from our vector up here. We're going to increment our count accordingly of nums. It will just be num in this case because we are doing a for each loop to count everything that we have already visited and the frequency of their elements. And for step 2, we're going to create a min heap to keep track of everything, which is just a priority queue. Int
vector pair int. Make sure we get this right. And then we're gonna have greater for a pair of int. Yep, right over here. It should be the third one right here. And then we'll have our min heap. Now, for the next step that we will do, is that this will be steps 4 and 5. Is that for 1, we're going to loop through the hash map and add each element to the pair. So we're going to have auto and I for the frequency of all of the all the elements that we have visited. So what we were doing is that we are going to push the frequency inside dot second. Alright, dot first. If the, this would be 5a. If the min heap size is going to be greater than k, then what we will be doing is that we're going to be popping. We're keeping track of all the frequency of the elements. The smallest element. From the heap, because we want the great. We want k amount of elements, not the smallest. We're going to do step 6. So what we're going to be doing is that we're going to have a vector called result of k number of frequency of elements. And so we're going to be scanning throughout the rest of our given array relative to the k number of elements, and then I is going to be greater than or equal to 0 because we're starting at the very end. Then we're going to decrease our way. And then we'll have our result of I equal to the min heap at the top with our second. And then we're going to have our min heap pop accordingly to be able to have the k most frequent elements. And finally, we will return our result. Oh. We're scanning our queue. Priority queue in step 6, and this is how we scan our queue. We're going to start at the end. I'm going to put all these notes in the comment section to be able to help further explain. But this should be the steps that we would need in order to have our problem already solved. So let me just run this.
All right, it passes all the test cases and submit. All right, and just to be able to give a rundown on our space and time complexity for the following is that the time complexity for our solution is going to be O of n log of k, where n refers to the length of the array, and this is because first we traverse the array to count the frequency of the elements, which is going to be O of n, and then we traverse the hash map and perform the push and pop operations in the min heap, which is going to be log of k. Hence, the total time complexity is going to be O of n log of k. Well, the space complexity for our following solution is going to be O of n, where n is referring to the length of the array, and this is because in the worst case scenario, all elements in the array are distinct, and both the hash map and the min heap will contain all these elements, hence the space complexity will be O of n. And yeah, okay, and this is the top k frequent elements. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe, and if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone. Today we're going to go over the problem unique paths for some Blind 75 C++ Leetcode. And now, just to be able to give a rundown on everything, be sure whenever we are breaking up the problem to fully understand, we need to check what our input is, what data structure / algorithm / technique to use, what to do with the data, and what our output is going to be. Alright, and so, to be able to break down the problem, there is a robot on m times n grid. The robot is initially located at the top left corner, grid 0, 0. The robot tries to move to the bottom right corner, grid m-1, n-1. The robot can only move either down or right at any point in time. Given the two integers m and n, return the number of possible unique paths that the robot can take to reach the bottom right corner. Okay, so we need to return all the possible paths. Input, we are given two integers which represent a grid as well. Okay, so the technique that we're going to be doing is going to be dynamic programming, where we're just going to expand upon the variables and their relationships. And so we need to ask ourselves what to do with the data. So the first step we need to do is that we are going to actually initialize a 2D grid, which will be a vector inside of another vector of integers called dp. And the second step we're going to do is set the value of the first row and first column cells to 1, since there is one cell, and this is how we set everything up. And the third, we're going to loop over the grid starting from the second row and second column. And then for each cell, I'm going to set its value equal to the sum of the cell above it and the cell to the left of it. And we are just going to finally return the number of unique paths, which would be represented as our grid that we have created, m-1, n-1, as the exact values. Okay, so first things first, we're going to do step 1, which will be vector right here, vector int dp m vector int, and then n. Then we're going to do step 2, initialize our rows. for int I is going to be equal to 0, I minus m, I plus plus, dp of I 0 equals 1 to start. Then for int of j is equal to 0, j minus n, or sorry, less than n, my bad. Sorry about that. J plus plus is going to represent our column, dp of, hence the x and the y, j is going to be that, x and, so this would represent our x, and this represents our y axis, and this is what to do with the data. This is step 3. We're going to loop through everything, so this is when we are reaching the first step, m I plus plus. We treat it as like x and y accordingly, which is why we do this. Then we're going to do the same thing because it's going to be a pretty unique operation of this will be when the robot moves over to the next column, n, which is also going to be our y-axis, and j plus plus. Then we're going to have dp of I and j equal dp of I minus 1 and j minus 1 right here. And then finally we're going to return our whole unique set of elements, or sorry, unique set of paths. So it's going to be dp of n minus 1 and then n minus 1. Let's see if we get this right. Make sure everything is spelled correctly. Here we go. Passes all the test cases. Just going to clean this up for you folks so that way you folks can actually see it. Okay. Alright, here we go. Alright, it passes all the test cases. So, to be able to give a rundown over exactly our solution and such, is that within our following solution, the time complexity is going to be O of m times n, where m represents the dimensions of the grid on the x-axis, and n is going to represent the dimensions of the grid on the y-axis. And then space complexity is also going to be the same at the same time, depending how large the entire grid is. Our space complexity is also going to have said complexity at the same time. And since we're also using a data structure of a vector, in this case, to keep track of all of the integers in the path that we have visited, this explains for our space complexity. So yeah, this was unique paths in dynamic programming for C++ Blind 75 Leetcode. Thank you again for taking time to watch this. If you found this helpful, feel free to like and subscribe. If you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers.
Hello everyone, today we are going to be going over the Blind 75 in C++, and today we're focusing on the problem valid anagram. Now, before we get started, whenever we are breaking down a following problem, we always ask ourselves these following 4 questions. What are inputs going to be? What data structure / algorithm / technique to use? What to do with the data? And finally, what are outputs going to be? So, to be able to break down our following problem, and also feel free to pause the video to be able to write these down while we're coding along. To break down the problem now, given two strings s and t, return true if t is an anagram of s and false otherwise. An anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. So in our first example, we have the input of s is equal to anagram and t is equal to n-agram. Whenever we rearrange the words all together, will it be the same? And so we already found that these are the same word, and so it's considered true. Our second example has the input of rat and car. Though we have the same number of characters, These are totally different words in particular because they're not the same characters. And so we also have our constraints. S and T consists of lowercase English letters. That's good. And so to be able to give a breakdown from a problem, we already know that we have two strings, S and T. And the following data structure / algorithm / technique we're going to use one map to keep track of the frequency of characters for both S and T. And what do we do with the data? It's going to be the following steps. Overall, we will keep track of each character in our maps to determine if they both have the same number of characters and the same type. So the steps that we need to do is that first we need to initialize our map to keep track of the frequency of similar characters between variables S and T. Then the second step, we are going to loop through the S string and increment the frequency of characters for S. Then the next part, we will loop through each character in string T. In doing so, we will decrement each character and the frequency map. And overall, finally, if there is a non-zero number, we will return false if the frequency map didn't turn to 0. So now, to be able to give a full rundown of our following solution, it will be this. So let me just move this up here just for reference. So now we're just going to be able to create our first map, an ordered map for character, integer, and then frequency. We'll just call it frequency of S over here just to specify, or we can just call it frequency A to indicate for the whole set of strings altogether. We can call it whatever. And then what we will do is that we are going to be, so this is going to be step 1, step 2, step 3, step 4. For step 2, we're going to be doing a loop through each of the characters within the S. So character right here, S, and then we're going to increase A per character. Let's say right over here. Then we're also going to do the same thing for our T. Loop through string T. This is going to be looping through string S. Step 1, we set up our map to keep track. And so we can literally just copy, paste this right over here, except for the key difference is going to be we change the S to a T, indicated by the parameters up here. We notice that we have a Boolean of S, and we also have T as well, so we can call upon them for our solution. And then, but mind you, we're also going to be decrementing as well, and decrementing the count to see if we actually have the same amount of characters. Now, what we will be doing is that if any count in our frequency is non-zero, we return false. So for auto entry of frequency S, if the entry that second doesn't equal 0, we're going to be returning false. We go down, and then finally we'll have our step 5, which is return true if S and T are anagrams, and false otherwise. So overall, we will return true. I'll specify this over here. True if an anagram. There we go. If true, return our anagram. No, well, we don't return an anagram. We return true if we found an anagram. There we go. So let's just test this bad boy out. Make sure it passes all the test cases. And we have a bit of a error. Auto entry. Let's see. Apologies on that. I misrepresented. I just added the wrong syntax. There we go. It passes all the test cases, and let's submit. Okay, and so to be able to give a breakdown on our full solution as well, let me just clean this up for you folks so you actually see what we were talking about. I'm also going to post this in the description as well for our solution. So the time complexity for our given solution is O of n, where n is the length of the input strings, and of S and T, where we iterate through each character once to build a frequency map. The space complexity, on the other hand, is O of 1, because the frequency map will have a fixed number of entries based on the character set. In this case, the character set is assumed to be lowercase English letters, which has a constant number of characters. And overall, we have a pretty optimal solution, as also indicated over here. And yeah, so this was Valid Anagram. Thank you again for taking time to be able to watch this. If you found this helpful, be sure and feel free to like and subscribe. And if you have any other questions or comments, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone. Today we are going to go over Valid Palindrome for some Blind 75 C++ code today. And now, before we even get started, I'm just going to write out exactly what we need to do to break down the question. So we have our input, what data structure / algorithm / technique to use, what to do with the data, and then our output. Alright, so now breaking down the question. A phrase palindrome is after converting all uppercase letters into lowercase letters, removing all non-alphanumeric characters. It reads the same forward and backwards. Alphanumeric characters include letters and numbers, such as given to string S, return true if it is a palindrome, or false otherwise. So let's look at an example. So input, we are given a string, and you can even look at the parameters at the same time up here and break it down, and it looks like we will return a true or false condition, and booleans are set to true. Default. And false otherwise. Well, if we set a condition, turn. Alright, so a man, a plan, a canal, Panama. True. Such as like, okay, so it's like, damn it, I'm mad, spelled backwards is damn. Damn it. I'm mad. There you go. Yay! Damn it, I'm mad. Spelled backwards is damn it, I'm mad. Oh, damn! That's a palindrome, for the most part. Okay, so that's the same thing. We gotta check to see if it is a palindrome or if it's not a palindrome, because all the letters Okay. Race a car, and this is not a palindrome. Because it needs to be the same type of word forward and backwards. Alright, and that's the same. Space, that is also a palindrome, just looking over example 3 as well. Alright, and so the technique we're actually going to be using this time is going to be 2 pointers in this case, where it's not, or 2 pointers, you literally have 1 point at the end, you have your left and your right, and it's like binary search, but it's not binary search because 2 pointers is not divide and conquer, and you don't have a middle type of variable whatsoever. You literally just have 2 pointers where it's just going to be your left and your right of your string. And it looks like what we're going to be doing for our steps is that we're going to initialize our 2 pointers left and right. Then what we're going to do is loop until we're going to be expanding upon the relationship between left and right pointers, and it looks like what we're doing is we're going to move the left pointer towards the right until it points to an alpha numeric character. So left is going to increment. And then we're going to move the right pointer towards the left until it points to an alpha numeric character. And then if the left and right pointers are not the same, we return false. We move the left pointer 1 step to the right and the right pointer 1 step to the left. And we would just be returning true as our default. Alright, now just to be able to go over our entire pseudocode steps, we're going to be doing first initialize. Left is going to be 0, and then int right, since we want the rightmost of the string, it's going to be s.length -1 accordingly. And then we're going to expand upon the relationship of them. While left is less than right, what we are going to be doing is while left is less than right, and this is also called from the STL library, is an alinum, is one way to be able to check between the 2 pointers from the STL library. Right over here, we're going to increment our left and make sure you have your semicolons and such, and then we are going to move while the left is less than the right, and this is also accounting for the right side. Right is going to decrement until we have reached them all together, so we can discern exactly if it's a palindrome or not. And by default, given the fact that we even have an empty string as one of the examples, we will then return everything to true. And now we're going to be focusing on the left side by using toLower, which is also a technique called from the STL library. Left if toLower is not equal to, if the left is not equal to the right, which it should be, as right, we're going to return false. And then accordingly, until we reach them all together, we're going to move the left pointer up and the right pointer down. And by default, we are going to be returning true right over here. Make sure it's all right. Make sure your conditions are all set. All right, it passes all the test cases. Let me just clean this up for you folks. All right, here we go. Let me just double check. Remove the white space. Just good practice. Here we go. And it works. Okay, now to give a rundown of our space and time complexity for the following. So our time complexity, given the fact that we are dealing with string and we're also dealing with the number of characters that we're also scanning through at the same time, the time complexity is going to be O of n because of the nature of the string, and the program will also run in accordance in constant time with the string, because as the string gets bigger, the time for the program to actually complete will also get bigger as well. And then for anything with space, since we're not using a data structure to store anything, it's going to be linear O of 1, since we're just scanning through the entire string for every single character. And yeah, that was Valid Palindrome. Thank you again for taking time to watch this. If you enjoyed this, feel free to like and subscribe. If you have any questions, feel free to put them in the comment section. And as always, cheers. Take care. Bye-bye. Hello everyone, today we're going to go over some Blind 75 Leetcode in C++ today, and today we are working with valid parentheses. Now, before we get started, always breaking down our question to understand the whole context fully. We gotta ask ourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and what our output's going to be. So now breaking down the question, as I'm just adding more comments for spacing, so we can fully understand what we're working with. All right. Now, given a string S containing just the characters of 3 different types of parentheses, it looks like. Right here, we got 1, we got 2, we got 3. Determine if the string is valid. An input string is valid if open brackets must be closed by the same type of brackets. Open brackets must be closed in the correct order. Every closed bracket has a corresponding open bracket of the same type. And then we have a following input. Right here, that would be, if it's actually parentheses, we're going to return true. And then if, in example 2, all the parentheses are closed and they're all corresponding, so it's also true. But in this case, in the third one, it's not, they're not the same brackets, so it's going to be false accordingly. So it looks like all together we are given a string and we need to return true if valid parentheses false otherwise. S consists of parentheses only, ... And we also need to false otherwise, and we also need to check for edge cases if there is no string as well. No characters. And the string as well. Yeah. Okie dokie. Right here. So now the technique I will be using is we'll be calling upon a stack. And if you are curious and wondering what a stack is, it's a type of data structure that, much like in a stack of plates that have various methods of push, pop, and then such as push and pop on a stack. Namely, one is able to actually organize their data accordingly, depending on exactly how they want to keep track of what has been scanned. So we will use the stack to keep track of all the characters visited. And what are we going to do with the data? Well, first things we're going to do is that we're going to initialize our stack. Second step we're going to do is loop through the string for every character. And then for all of the beginning parentheses, we will store the characters in the stack, and then for the closing parentheses, we're going to check to see if the top of the stack has the corresponding character. If they are matching, if the stack is empty, or it's not or the character is not matching at the top, we declare false. And then if the closing parentheses matches the top of the stack, we're going to pop the top element from the stack. Because the reason being that we are going to be popping the stack in particular, like say for instance that we have a given character right here inside our stack. If we add this one to start, and then we are going to remove this one, and we're going to check to see if the next one inside of our string for the character is going to be matching. If it's matching this, then we will be returning false. Then if it's also corresponding with this, then we're going to continue at the same time with our given character, because for scanning the entire string, we can just focus on one entirely, and then we can just move over to the next one as well. And by Boolean conditions, by default, it's true. And then we also have a method if the character is matching. So we had a number of questions really when understanding more between the characters. Is that what we will be doing? We're going to create a separate method really that's going to be called upon within our main type of main function, so that way we can actually see what is corresponding and such. So we will have a boolean, since booleans are default by true. We're going to set our conditions. So this is what I will be doing. So we are going to create a private bool to start, which will be the character of open, character of close, and then we will return. It's going to naturally return true, so we'll have open dot 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 right here, and close is going to be right here, or right here. So this will actually help us. This will actually set our conditions already in place. Be sure I got this right. and that way we actually determine what's going to be open and what's going to be closed as well. Alright, so first things first, I'm going to initialize our stack for characters. Call it SDK, and we're going to loop through the entire array for car C of S right here. What we will be doing is storing all the characters inside the stack, and the way we do this is we're going to use push. But then we also need to check if C is going to be equal to here or push that. Else if we will be checking to see on the other characters as well. Then our other condition for stack is empty, and if it matches what we put in the stack, excuse me, empty or SDK or what is matching SDK.top for character. No. Right here, we will then return false. SDK top. Or pop over here. We will pop the stack. And we will return SDK.empty, since we already have the condition of what is true and then what is also false as well. Okay, let's just see if it all works. I'm sure I got everything right. Looks fine to me. There we go, it passes all the test cases. I'm just gonna clean this all up for you guys. Ugh. Empty, and then it will be called by here. We will therefore empty be false. There we go. We will pop the stack accordingly. Okay. Let's just double check. Pass all the test cases. Alright, and it works. Okay, so now to just give a rundown on everything over what we have already done is, so given the fact that we're using the stack, the time complexity is going to be O of n, where n is the length of the strings relative, and given the fact we're using a data structure, n is going to be set stack, and however, since we are using the data structure, the space complexity is going to be O of n for the most part, and so just give a rundown, time complexity is O of n because it's relative to the size of the string, and then the space complexity is O of n because we're using a stack. Alright, and so this was Valid Parentheses. Thank you again for taking the time to watch this. If you found this helpful, feel free to like and subscribe. If you have any questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye.
Hello everyone, today we will be going over the blind 75 in C++, and today we're working on validate binary search tree.
Now, before we get started, make sure that we already have our 4 questions already laid out to break down the problem. We need to ask ourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and what our output is going to be. So, to go over the question, given the root of a binary tree, determine if it is a valid binary search tree, where a valid binary search tree is defined as follows. The left subtree of a node contains only nodes with keys less than a node's key. The right subtree of a node contains only nodes with keys greater than a node's key, and both the left and right subtrees must also be binary search trees. So, to break down the following question, what does it mean by node's keys or node with keys? Well, keys is just another term for saying, hey, this is the value of the following subtree. So just by nature of binary search trees, nodes that are going to be less than the node's key or the node's value that we have with the current one, it's going to be on the left, and then greater is on the right. That's just based on principle. Binary search trees by principle. Left is less, right is more. That's just what they mean. And we just need to replicate this entire behavior and nature of the binary search tree just to determine if it's actually true. And it looks like we are just given the root of a binary tree. And then our output is that return true or false if we have a valid binary search tree or not. So, the technique that we will be doing for the following case is going to be recursion. We will create a helper function to determine the current node, the minimum allowed value, and the maximum allowed value. And to go over the steps of how we will replicate this, one, we're going to call upon a helper function we will create and then call upon throughout the rest of our solution is a valid binary search tree with the root node and the minimum and maximum allowed values. Those are going to be some parameters we're going to create. And then step 2, we're going to create our helper recursive function that takes the current node, the minimum and max values. Then we're going to have a base case. If the current node is null, we're going to return true, and the reason being, and even in the case of an empty subtree, it is also considered true. Then we're going to check if the value of the current node is within the allowed range, greater than the minimum and less than the maximum. If not, return false. Step 5, we're going to recursively check the left subtree by calling our helper function with the left child, the minimum allowed value, and the current node, which is set to be our maximum value. I'm just calling it max value for short. Then we're going to do the same thing on the right side. Five. That's what we will do. First, we check on the right subtree by calling our helper function, and which is set to be our max. Right there. So we're just going to do left and the right. And then finally, we're going to return the logical operators. We're going to return the logical and of the results obtained from checking the left and right subtrees, as well as the validity of the current node to see if it's actually our max value. So now to break down everything that we will do, just going to go out the steps. And since this will also be our output for our main type of function, we are going to have a helper function that's going to be called. So this is step 1. Return is valid binary search tree helper. We're going to have a root, our left, which we will set as null, and then our right, which will be default. And then we're going to create our helper function, which will be step 2. Private Boolean is valid binary search tree helper. We're going to have a tree node as a parameter, which will be the node for the root. Then we're going to have a tree node for our min node, and then tree node for our max node, because we know the relationship between them. Because anything that's going to be less is going to be on the left, right is going to be more. That's just the nature of binary search trees. Then we're going to have a base case that we're going to do. So that's going to be step 3, where if we don't have any node whatsoever, it's going to be a null pointer. Then we're going to return true in this case. Then we're going to check the value of the following range, which would be step 4. If, okay, min node and node value is less than or equal to the min node. Let me just correct that right here, val, or we'll do the same relationship for max node. Node and node value is greater than our max node. Over here, we're going to return false, because we need to set up the entire behavior and relationship with left being less and then right being more at the same time, which is why we are doing this. Alright, I'm just going to put this right here. Check if the current node is within the allowed range, greater than minimum. So, this will be in the case where greater than the minimum. And then greater than minimum, less than maximum. That's what we do. And what we will do with the data, we're going to do this for the left subtree, which will be if, and we're going to call upon our helper function, valid binary search tree helper, node, left, min, node, node. We're going to return false. Then we'll do the same for the right. Which will be our max node, and then max node. Hence, min node is on the left, max node is on the right. That is what we have. Yes, yes, yes. And then in any other case, we will have for step 7, return the logical and operator results of the right and left subtrees. If everything's already checked out, and the validity of the current node, where all we have to do is just return true, because we already checked the following cases where everything is false. So by default, we will return true in this case. And I'm just going to make sure we have everything already right. If there are any syntax errors. Step 4. This is in the case where it is not valid, hence the exclamation mark that's already right there. All right, make sure you have this. All right, it passes all the test cases. Let me just clean all this stuff up for you folks. All right, submitting it. Okay, and to just give a breakdown and rundown on our space and time complexity for the following solution is that our time complexity for the following is going to be O of n, where n is referring to the number of nodes in the binary tree, and we visit each node at least once during our recursive traversal. And the space complexity is going to be O of n, since n also refers to the number of nodes in the binary tree. And we're using a recursion stack to be able to store everything that we have already visited for our nodes and then checking to see if it's true or false. Recursion typically would just be O of n by nature. And yeah, so this was validate a binary search tree in C++. Thanks again for taking time to watch this. If you found this helpful, like and subscribe. And if you have any other questions, please put them in the comment section. And as always, take care. Cheers. Bye-bye.
Hello everyone, today we are going over the line 75 in C++, and today we are working with the word break. Now, before we get started, feel free to pause the video if you would like to follow along to write step by step with me over exactly how to go about this problem and solve it accordingly. And for every problem, we need to ask ourselves these 4 questions: what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and finally what our output's going to be. So, just to give a breakdown on the whole problem, we are given a string S and a dictionary of strings word dict. Return true if S can be segmented into a space separated sequence of one or more dictionary words. Note that the same word in the dictionary may be reused multiple times in the segmentation. Okay, so if we have Leetcode, for instance, we have Leetcode being true, just for this example, and the reason being because return true because Leetcode can be segmented as Leetcode. But in this case, apple and word apple, pen, apple. Okay, so we have apple, pen, and apple pen. It's kind of like the one video. Anyway, and then we return true, and then return true because apple, pen, apple can be segmented as apple, pen, apple. Note that you are allowed to reuse a dictionary word, okay? And then we have cats and dog with a word dict of cats, dog, sand, and cat. And it's false, namely because, hey, we have cats right here, and then we are just left with OG. It looks like all the words, accordingly, still need to be intact. We can reuse them, but all the words need to be stayed intact. So, just to break down our input, we are given a word S and a dictionary of strings called word dict, and it looks like our output is either true for if we can find the word in our word dictionary, or false otherwise. Alright, and so the technique to be able to solve this following problem is that we're going to use dynamic programming, where dynamic programming, best way of describing it is basically what we will be doing is that we will be going forward and backward within a word dictionary to be able to find every single character that we find to be able to make up our following string that we are given. For apple, pen, apple, we're going to have to go forward. Then we'll also have to go backward to be able to find exactly each word that will add up to our following word that we are given. So each word from the word dictionary will add up to our word we are given. And so the steps for us over in principle, what we will need to do is that we will overall use a dynamic programming array to keep track of whether a substring of the input string can be segmented into space separated sequence of dictionary words. We do that. And so the following steps that we would need to do in order to actually accomplish this task is that one, we need to initialize a DP array of Boolean values, DP. Then second, we need to set dynamic programming the array to be true just to initialize, and then for every substring we're going to check if it can be segmented into words from the dictionary. Start. For the next part, if the entire string can be segmented, we will have dp of s.length, the length of the following string that is already inside of our dynamic programming array will be true. And then finally, what we will be doing is that we will return our array that we created, s.length, okay. Now, the way how this will look accordingly, just to have our following steps. Let me just clean this up and just set up for you folks. As that for step one, it's going to look like this. I'm going to vector bool for dp size +1. We're going to set this to false to initialize. Then we're going to have step 2 to initialize our array at the beginning. dp equals true. We have our following Boolean that we are initializing right here, and then we're going to do step 3. For every substring, we're going to check if word dictionary for each word can be segmented. So to do so, we are going to have a nested for loop. Int I is going to be 1, I less than or equal to s.size. I is going to be incremented. And then we're going to have another one, int j is going to be equal to I minus 1. J is greater than or equal to 0, and then j is decremented. Then if dp of j string word equal s dot substring of j I minus j. This is where if the entire string can be segmented accordingly, we will set this to be true. So this will be step 4. Find word dic at the beginning, word dic at the end for each word that we have. It will be the substring for when we're scanning throughout the rest. If it doesn't equal, and we're going to set our current index to true for this case, and then we're going to break for we have already found our true statement. Since we already found out that these can be segmented as well. That is really just the main thing. If we can segment our following word dictionary from the start and end with our word. And then finally, we will return array with the following word size. Let me just double check to see if it's right. Don't forget this. And that. Okay, passes all the test cases. And just give a breakdown on the space and time complexity for a following solution is that the time complexity is going to be O of n squared times m, where that would be in the worst case, where n is the length of the string and m is the length of the longest string in the dictionary, and we use 2 loops of O of n to generate substrings, and for each substring, in the worst case, we may check a word of length m in the dictionary, while meanwhile the space complexity for a following solution is that it will be O of n for just in regards, since we're using an array to store everything. Alright, and so this was Word Break. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comments section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we will be going over the blind 75 in C++, and today we are working with the problem word search number 2. Now, before we get started, in order to break down the following problem, and if you're also following along at home or wherever, we need to ask ourselves these 4 questions in order to break down the following problem. We first need to ask ourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and finally what our output's going to be. So, breaking down the problem, given an m times n board of characters and a list of strings called words, we already know what our input is. Return all the words on the board. Alright. Each word must be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter may not be used more than once in a word. So if we have a following input of characters that we have, we need to find adjacent characters coming together where there will be a staggering connection for the following. And so what we will do for the following technique is that I'll also put links for the following videos as well in the card section. Just press the I icon on the top right corner. The technique that we're going to be doing to be able to replicate this following behavior is going to be a try data structure with depth first search. Now, why do we do this? Well, given the fact that 1, we are dealing with a board of characters, which is a list of where we have a board of characters, and then we also have the words oath, pee, eat, and rain, for example. We're just trying to find these words inside the list of the characters which are adjacent to each other. So we are trying to find the words with the given board of characters to find which words are in the board where the characters are adjacent to each other. And so the steps for us to be able to accomplish this for the following task are going to be the following. Step 1, we will initialize a try data structure and insert all the words into it. With each character. Step 2, we will create a list to store the found words from our character board. Step 3, we will loop over
each cell in the board using def first search for both the row and the column. Step 4, you will return the list of found words. So, just going over all the steps that we need to do. I'm also going to further expand this at the same time. So, step 1, what we will do ultimately is that to initialize a try data structure, we will need to do the following. Create a separate structure to initialize the try node, children, and word. So if I'm going step 1, step 2, step 3, step 4, step 1 is going to look like the following. We're going to move this out here so that way we can call upon a public struct that we have, where it's going to represent try node, and then we're going to have a vector or try nodes for children, and then we're going to have a string called word. Then we're going to have a try node structure with children ranging from the English letters in the alphabet with a null pointer, and then word. This is just how we initialize our following. Don't forget the comments as well. And this is just how we set up everything with a try node structure. Now, what we will do for step 2 is that we will initialize the root of the try node, and then we will scan every word in the words list we are given. Scan every string in the words list we are given. That's a better way of putting it. And we will scan every character we visit in the word list. Then create a new node for each character in our try node structure to add what we have visited and we will move to the child node representing the current character. And finally, we will store the word at the final try node. And the way it's going to look like for step 2, we're going to do the following. A, B, C, D, E, F. Step 2 is going to look like this. Try node, root, new try node,
then B for string and word for words. We're gonna reinstantiate try node for node. The root. And we will scan the characters. Create a new character for So the way we are going to do D is that we're going to set up, assuming that we have not visited children for C, A. I'm going to set that equal to the null pointer. So, node children for character, each one, we'll go to new try node to add to the structure, calling upon it, yes. Then we have E, where we're going to move the child node represent the current character. The way we do this is node equal node children C A, and store the word of the at the final try node for F. So node word. Then heading over to step 3. Is that we will create a list to store the found words. B, we're going to loop over each cell in the board, row and column, and inside we will perform def for search, and I'll also highlight how we will create our def for search function for later, but for the meantime we're just going to loop everything that we've already visited. So we will have a vector of strings, which will be our result, to store everything that we have visited. So for int I is equal to 0. I is less than the board size, and I is incremented. And it's for the row, and it's for the column. Int j is equal to 0. J is less than the board at the following index, and then size to indicate for this. Rows and columns, yes. Double check. And while doing so, we're going to perform def for search for a board I, j, root, and result. And this will be our function that we're going to create right over here. Def for search function. Yep, that's what we do. A, B, C. All right. To A, I'm just going to specify 2, 2, 2, 2, 2, 3, 3B, and then 3C. There we go. That's more like it. Just helping out with everything else. And then we will return a list of words, so it's going to be return result, which is our list we created over here. Now for the def for search function. Now the way it's going to look, I'm actually going to put this over here so we can go step by step accordingly for how this whole thing will be built is that for our def for search function, we're going to check if the current cell is visited or the corresponding try node for the current character does not exist. If so, if we have visited or is the corresponding try node we will just return nothing, and we're going to move along to the next node and then check if the current try node contains a word. If it does, we add the word to the list of found words and clear the word from the try node. And then we mark the, let me just put this right here. 1, 2, 3, 3A, and then we're going to mark the current cell as visited, and then we will recursively perform def for search, where there's going to be an element of recursion with recursion of the neighboring cells in directions up, down, left, right. So this is how we're going to build our def for search function. It's going to be a private void def for search with the following parameters that we created up here. So it's going to be vector for characters, and board, much like in the case over the parameters we have right here. Interestingly enough. Then we will have I, which will be int I, and then int j, and then try node with a vector, string, and result. There we go. Just double checking, because we're going to take the rows and the columns while scanning through and showing the root to ultimately get a result. Much like in the case of taking the parameters that are right here, except where we have result that we will be returning instead of the words. So while scanning through them, we have step 1, step 2, step 3, step 4, and step 5. So step 1, what we'll do is that we first need to initialize our character at the given index. So we need board I and j, just need to specify that. First initialize the current character at board, row, and column. Then okay, and then for 1A, right, if the current character has been visited, we're going to mark it like this with the pound, indicating that it is visited, or the node children for C and A, indicate nothing's there. We're just going to put in return to indicate, hey, we don't have anything there. Then for the next step, we're going to move along to the next node. The way we do that is that we're going to do node is equal to node children C root A. And then what we will do, check if the current tree contains a word. We do so by the following: if the node, if the node for the word is not empty, indicated by the exclamation mark over there, then what we will do is that for our list that we have result, which is in a public structure that we're able to call. So we have result pushback for our node to word, and then we have node word right there. Step 4, we're going to indicate if the board has been visited, so we do so with ij is equal to the pound. Then we're going to indicate for our directions up, left, down, or right. So this will be for the following. If I is greater than 0, def for search board I minus 1 j, then we have the node and the result. Also, quick correction. So this will be for all of the directions that we have. Pause here. Okay, so this is how we do the directions. Just want to be sure on that. So up, down, left, and right. So I is going to be the key indication for every single row that we have, and J represents the column, so yes. So for down, if I is less than the board dot size minus 1, we're going to do a recursive call with the board I plus 1, and just move up accordingly J, node, and result. Make sure that we always have our semicolons. And then we'll do the same thing, except for it's going to be the left and the right, and we're going to deal with J. So J is at the very left, and then it should be J minus 1. And then for the right, if J is less than the board size minus 1, yes. So we have j plus 1. Yep, node result. Alright. Dealing with I, yes. Dealing with J, just being sure if we have everything all correct. Okay, so this should be the result that we have. I'm just going to put these notes up here to showcase to you folks what we need. And just put this right here. There we go. Alright, avoid all of that. Here we go. That's more like it. Right there. Blah, 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 blah. And I'm going to keep all the notes together and then also showcase to you folks anything else. So this is where our depth for search solution, just trying to get it in frame. If I can like do that. Okay, there we go. Let's double check on everything. Alright, so we have a syntax error. Make sure you keep your semicolons. And we have a runtime error. Yay. Okay, also for the right, given the fact that we are dealing with J, we have to be right here, over there. That makes sense. I forgot the 0 index to start with because board, since I represents rows, J represents columns accordingly, this should work. Nope. I also forgot to make this J. Alright. And there is one specific part that also needs to be added. That's the very last step for this. Part 6 is that we need to revert the current cell to its original state, indicating we have not visited. So, it should be looking like this. Board I of J is then equal to C, indicating that we haven't reverted the cell back to its current state. So let's try this again. Alright, it passes all the test cases. Let's submit this. Alright, okay, we have the whole solution already set up in place. Now, to give a breakdown on the space and time complexity for our following solution, is that our time complexity for the following is going to be O of M plus N, where O of M is the total number of characters on the words, while N is the total number of cells in the board. And meanwhile, the space complexity for our following solution is going to be O of M plus L, where O of M refers to the total characters in all the words, and then L represents the stack for what we use based on the size of the given board and the length of the word, respectively, to each. So yes, this was Word Search 2. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we are going to be going over the blind 75 in C++, and today we are working on the problem word search. So, before we get started, make sure that we always have to have out of 4 questions. We need to ask ourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and what our output is going to be. So, breaking down the question that we have, so we are given an m times n grid of characters, board, and a string of words. Return true if a word exists in the grid. So that's easy to break down. So we are given a matrix, m times n. We can even look at the parameters up here. We were given a string for word. And it looks like for the problem, the word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring the same letter cell may not be used more than once. Okay, so if we were to go over this example, we have the input and the output. So we have a board of A, B, C, and E, S, F, C, S, A, D, E, E. And we have a word A, B, C, C, E, D. We have to see if it's all connected within our given matrix that we have. So
when scanning throughout the rest of the matrix, is the word in there? And if it is, it looks like for the result, it would be true. And then for example 2, we have a given matrix over here, and then we have the word C. Is it all connected? Well, according to this one, yes, it's true. Now, if we have this one, A, B, C, B, as this word within the board, is it really connected all together? Well, in this case, it's not. So what we need to do is we need to replicate this behavior to be able to have our input or output exist accordingly. So we would need to return true if the word is in the matrix accordingly. And the technique we will be using for this is going to be depth first search with recursion to check for each matrix that has been checked already. And so I'm going to break down depth first search in the following steps that we have for what we are going to do with the following data. So to be able to break down, I'm going to first expand in 3 different steps. So one, what we need to do is that for our given solution, we need to loop over each cell in the board from top to bottom and right to left, accordingly using a nested for loop. And then for step 2, what we're going to do, we're going to perform depth first search by creating a function which takes in the parameters of the board, index of I, index of J, with our word and our current index. We therefore be returning true if the word is in the matrix. 3, otherwise return false in this case. And I'm going to be expanding a little bit more on part 2, namely to be able to break down our following depth first search function. So if we want to break down even further, so what we need to do accordingly is that 1, to perform depth first search, we need to check if the current cell is out of bounds, already visited, or the character does not match the current character in the word. If so, we return false. Then we're going to check if we have reached the last character in the word. If so, we return true. And then we're going to mark the current cell as visited. Then the next part is that we're going to recursively call, which means we're going to have a function inside of a function to be able to call to check for the 4 directions of up, down, left, and right. So we will recursively perform depth first search on the neighboring cells, up, down, left, and right, that are within the board's bound. If any of the depth first search calls return true, will return true. And then we're going to revert the current cell to its original state as unvisited. So now, to be able to go over exactly what we've discussed, all right. So first thing we're going to be doing is that we're going to be looping throughout the rest of the matrix, which means most likely we will use a nested for loop for int I is going to be equal to 0, I is less than the board size. And then I plus plus, and then we're going to do the same thing for the other direction as well. We're going to use j. J is going to be less than the board dots of the very first index and the 0 index size. Then j increment as we were scanning throughout the rest of the board. Then what we were going to be doing is we're going to be creating this function. Our df is called with our parameters, and this is how our depth first search function is going to be checked in place. If the depth first search function with the board already taken into play with respect to the I index and j index of our word, the 0, representing the index as well, then we're going to be returning true, and then otherwise we will be returning false. This case. So now what we will be doing is now creating our depth first search function, which will be called recursively for our following. So we're going to have a private function, which will be a Boolean. Depth first search, which will be a vector. We can literally take the same stuff on the board up here. Board int I, int j, string, and word, int index, if I is going to be less than 0, or I is going to be greater than or equal to the board size. Since what we are doing right now is that this is what we will be doing right over here. This is our Boolean condition to be able to check the following requirements. So check if the character is out of the bounds, already visited. J is going to be less than 0, or j is greater than the board size. I'm checking to see if it's out of bounds, or board I and j is not equal to the following word that we have found at our index, which is our string. Therefore, we're going to be returning false. Then I can to see if we visited the last character in the word. If so, if the index that we have is going to be the very last character of the word, -1 accordingly, and then we're going to be returning true in this case. Then we're going to mark current cell as visited, character temp board I j, the board accordingly. We're going to have this be our divider. I know this may be a little bit out of context for a second, but this represents the characters that we have already found accordingly. And recursion. Search for our 4 directions. This is where we declare and how we initialize our board accordingly with respect to I and j. This is why we have it right here. This is to initialize our boards. Now we are going to be focusing on the directions that we have. So we're going to have a Boolean of found, which would be our def search function. Board I +1 j word index +1, or up, down, left, right, up, down, left, right. So then this is our up direction. This is going to be our down direction. right here. On this one, it's just going to be I in this case. I'm just going to put this over here. Left and right. Up, down, left, and right. So J represents our left and right. I represents up and down accordingly, which is why we have these two nested for loops while scanning throughout the rest of the matrix accordingly. Make sure we have this. Then we will revert the current cell. Then we're going to revert the current cell to its original state unvisited. So we're going to use this temp over here to indicate if we have not visited the following, and this will just be checking itself whenever we're calling upon this function and our given parameters as well. So temp here, I'm going to return found the result if it's true or false. Okay, let's double check to see if we have everything already set in place. I had a feeling there might have been a syntax error accordingly. Okay, so I found this error, and I forgot to put in this equal sign. I know this may be a little bit tedious for the syntax to be able to start, so hopefully this will work. All right, it passes all the test cases to start with. Let's submit. Okay, and it runs pretty efficiently. Let me just clean this up for you folks, so that way you folks can actually see the full problem accordingly. Boop, boop, boop. Boop. All right, submit this. Okay, so now just to be able to give a rundown and breakdown of our space and time complexity for the following solution that we have over here is that the time complexity for the following solution is going to be O of n times 4 to the 4 to the L, where n is the total number of cells in the input board, and L is the length of the word to be matched. And for a cell with one letter, the total time complexity would be O4 of L, given the fact that we are dealing with a matrix, and that's in the case of the worst case scenario. But since we're also doing this recursively, the depth first search would be performed to the depth of the length of the matrix, the word, and we would have 4 different directions to explore relative to finding said word. So 4 represents the length of the given word, and then n also represents the total number of cells in the board that we have. And meanwhile, the space complexity that we have for the following is going to be O of L, where L represents the length of the word that needs to be matched inside of our given array. Since 1, it will be constant, given the fact that 1, we are using a data structure, namely we're using an algorithm really in this case for depth first search, which utilizes a stack to be able to
keep track of every single element that we have visited, so therefore it will be constant, and L represents the length of the word, so the space complexity would be O about. So yes, this was word search. Thanks again for taking time to watch this. If you found this helpful, like and subscribe, and if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye. Hello everyone, today we are going to be going over some Leetcode today, and today we'll be focusing on search in rotated sorted array. Now, to give a rundown of the whole question of what we're facing is that we are given an integer array of nums sorted in ascending order with distinct values. Prior to being passed to your function, nums is possibly rotated at an unknown pivot of k, such that the result array is the following over here: nums k plus 1, nums n minus 1, nums 0, etc. The point is it's rotated at 0 indexed. For example, 0, 1, 2, 4, 5, 6, 7 might be rotated at pivot 3 and become 4, 5, 6, 7, 0, 1, 2. Given the array nums after the possible rotation and an integer target, return the index of target if it is in nums, or -1 if it's not in nums. Alright, so based on our questions, what we have to ask ourselves what the input's going to be, what data structure / algorithm technique to use, what to do with the data, and what our output's going to be. So we already know what the output is. We need to return the index of target if it is nums, or -1 if it is nums. So we already know exactly what we have to do. We have to return -1, and then what we need to do for our input nums with a target, as specified in our parameters up here, nums, and then we have target. We also need to write this algorithm in O log n time complexity. And overall, just from looking from the example, we have nums equal to 4, 5, 6, 7, 0, 1, 2 with a target of 0. And our output is 4. What we need to do is that we need to reflect the relationship of the following examples, example 1, 2, and 3, to have our input reflect our output. So if we have a target of 0 already started, it's actually located right here. So arrays start at 0 by principle. So 0, 1, 2, 3, and 4. The target is 0 right over here, and it's located right over here. So it's at index 4, which we output 4. And if the target is not located in the array, we're going to have to return -1, similar in the case of right here, and over here, and here. So I'm going to introduce you folks to a technique called binary search, where in it's more of a divide and conquer method, where we have 3 variables of the middle, low, and high end. And the way how we are going to figure out between the two is that with binary search, the principle is, say for example you have a row of cards. That's the best way of describing it. And you are supposed to find your given target. You have a value you need to find of 1. Now you don't know where 1 is already located because it's already been shuffled in the amount of cards. But what you can do is that if you have your following numbers already taken into consideration for the array, you can actually find where the middle is going to be located. And when you find where the middle is, you can actually get rid of the other stack of cards, and even right here and here, to ultimately find the card you're looking for. And this type of complexity runs O log n time. And the way how the variables need to be made is that middle is made with the following. So people would typically think it will be high minus low divided by 2, since that's just by nature how to get the average. But really, because we're working in C++ and to prevent an overflow, we have to add this plus low in the case of if we have an extreme variable that has a value that's really low or a value that's really high. And our low, we're going to initialize it as 0, and then a high value is going to be nums.size minus 1, because we're looking at the very last element inside of the array. And so what we can do, just based on principle, you have to first initialize our variables. 2, we need to expand upon the relationships between our variables, which will mean 2a, while low is going to be less than or equal to high. I want to redeclare our middle variable here, or it doesn't matter if you put it inside or outside the loop. You can declare it where in particular, that should be fine. But since we are working inside of a while loop and that we have an array of nums, what we need to do is that we need to check the edge cases if the target is middle, is in the middle. We're going to return our target, which will be our middle. If the target is on the left, we are going to shift our middle to the left, because really what we need to do is that we are going to be, this is where we will be returning our target ultimately, since we declared it as a middle. And then what we will do if the target is on the right, we will shift to our middle, which is on the right. So I'm going to now write the code out just to be able to further explain at the same time. So we're going to first initialize our variables. Int low is going to be 0, int high is going to be nums.size -1, and then I will go in this while loop. Low is less than equal to high, which will then be, once we initialize our mid, which will be low plus low, high minus low, divided by 2. We will then, if the nums of mid is going to be equal to the target value, we are then going to return our mid. And since we already have our mid already set in place, I will then have this variable for our left, and then for our right. Right, and then we're going to have some further edge cases as well to expand upon. Over here, so this will be in the case where the nums of mid is going to be less than or equal to nums of low. And then this is in the case for our right, in our rightmost area over here. Or actually, it's going to be nums of low is less than or equal to mid. This is for our leftmost. That makes sense over here. Not mid minus low, because the reason being is that we are trying to figure out where the target is. In particular, if it's on the leftmost side, it's going to be less than our middle variable right over here. All right. Now, else if okay, now then we need to, for the leftmost, if the nums of low is less than or equal to the mid, that means the target is going to be less than the nums of mid and the target is going to be less than or equal. It's going to be greater than or equal to the nums of low. Already, and low is going to be, high is going to be mid -1, and else right over here. In this case, if it's not there, then we're going to check the rightmost. Low is going to be mid +1 over here. And now we will go for the rightmost over here. Now, this will be the relationship of if nums high will be greater than or equal to the nums of mid in this case. And then we will have our edge cases if the target is going to be greater than nums of mid and target is going to be less than or equal to the nums of high, because high is the rightmost element that we have. Then low is going to be equal to mid +1, and else then we're going to search the leftmost, and high is going to be equal to mid -1 over here. All right, and I think this should check out from what we have. Over here, so we first initialize a variable is already here, then we have our while loop already set in place, that where our middle variable is already declared, and then we check accordingly. If the mid is equal to our target, then we return a mid. For our left, if the leftmost, we have to discern between the relationship of low and the middle, and then we have our edge case to determine if the target is below the mid and the target must be low, because we were searching for the leftmost, then the middle must be shifted over. Well, the high must be shifted over, and we then need to figure out in particular of where the target's going to be. We shift where the is, and we else not the condition. Move low up, and then we do the same thing for the below. It's just this is focusing on the right side, this is focusing on the left, this will focus on the middle. So I think this should be good. Let's just double check to see if everything's already lined up. And we return 1 if it's not nums. Not in our nums array. Alright, it passes all the test cases. And submit. There we go. And just to give a rundown on the space and time complexity that we have for our given solution, I will just further expand upon this. In fact, I'm just going to go back and then let me just clean this up so that way you folks can actually see what I'm talking about right over here. Just going to clean this up. There we go. So this is our pseudocode at the top, and this is our solution. So to give a breakdown of our space and time complexity, our time complexity, given the fact that we're doing everything in binary search, is going to be O log of n, and then our time complexity, given the fact we're not using a data structure already set in place, our space complexity is going to be O of 1 linear, given the fact we're not storing anything from our arrays, and the O log of n in particular is our time as requested from the problem, because we've already reduced the search space already from just focusing on the middle already, and we're not storing anything and calling upon a data structure. So yeah, this was search in a rotated sorted array. Thank you again for taking time to watch this. If you have any questions, feel free to put them in the comments section. And if you enjoy this video, like and subscribe. And as always, cheers. Take care. Have a good day. Bye-bye. Hello everyone, today we're going to go over some Blind 75 C++, and before we get started, make sure that we have our 4 questions already laid out to help formulate every single problem. So we always need to ask ourselves what the input's going to be. What data structure / algorithm / technique to use. What to do with the data. and then figuring out what our output is. So, to be able to give a rundown on the whole question, given an integer array nums, return the length of longest strictly increasing subsequence. Okay, so we will return the length of the longest strictly increasing subsequence. We were given an array nums right here. So we need to figure out the streak of how many numbers. It's pretty simple. Alright. To figure out the longest streak of numbers which are increasing. It's pretty self-explanatory. We have here the longest increasing subsequence is over here. This 4. And 7. So I'll just need to clarify for 4. Okay. So the longest form of increasing subsequence. You have 0, 1, and then 2, 3. 0, 1, 2, 3 for the entire thing. That would explain 4. We have 4 elements over here. So that makes sense. Just trying to clarify on that part. Okay, and with the technique we're going to be focusing on this problem today, we will focus on dynamic programming, because we will be moving forward and backwards in our array to understand the pattern and get our desired output. We're most likely going to have 2 loops to start with. Oh, going over the first step, we need to initialize an array called dp of nums size. We will, for clarity, declare int n is equal to nums.size. Three, we will loop over the array starting from the second number since we need a sequence. We will iterate also every number before the second number to have our sequence. B, we will declare our second number to be greater than our first number. Yeah, this will be in the statement. If our second number is greater than our first number, we will set our current index to get the max of number and dp of and last number stored in our dp array of the previous number plus 1. For our sequence. And then we will return the max value in dp from in our array from start to end to get the sequence. Alright, first things first, step 1 and 2, we're going to first initialize. Let's do P1. We're going to loop. And the second number in I is going to be 1. I is less than n and I plus plus 4. Then j is going to be equal to 0. J is less than I. J plus plus. dp of j, it's going to be plus 1 up here, this will be our index, C, 3b, we're going to return step 4, alright, we're going to return with max again, dp.end. Alright, this looks fine to me. Make sure you always have comments. Alright, passes all the test cases. We'll submit. And here we go. Alright, so just to give a rundown and breakdown of our time and space complexity is that, given the fact we're using a nested for loop, I'm looping the array twice. The time complexity is going to be O of n squared, where n is referring to the size of the array. And the space complexity, given the fact we're using a data structure of an array to store all of the elements that we have found throughout the rest of the array, it's going to be O of n. So yeah, this was longest increasing subsequence. Thank you again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comments section. And as always, take care. Bye-bye.